Hello, wonderful people of the internet. Welcome back to another episode of Leos Labs. So, we got a lot of stuff done yesterday. I want to talk a little bit about the schedule for today, and then we're just going to hop right into it. So, let me open up Zernal PP, talk about what we've been doing, where we have been, all this kind of stuff. So, obviously, anyone who might be lurking in chat, hey, thanks for being here, and let's move over this way. So, the stream title says the world's fastest fractal generator. The world's fastest fractal generator. World's fastest fractal generator. Okay, now here's the thing. There's always caveats here anytime you say something like this, and the caveat here is that we're working on a very particular type of fractal known as the iterated function system. The reason I think that the generated, fractal generator that we're going to create will be better than anything else the world has seen before is because, well, we're not going to be using a chaos game. We're actually going to be using a fundamentally different way to solve the iterated function system. Now, there's still a long ways to go before we're actually anywhere near this goal. And so what we've worked on so far are things like, a symbolic generator, symbolic expression library, we'll say. Which we're going to talk about more today. The other thing we've worked on is the fractal flame method. While we've also introduced a bunch of other things. So what are these guys? Well, the first is a way for people to express the equations that will turn into fractals. The second is basically a way to combine a bunch of equations together into a large superfractal known as a fractal flame. These two things put together will kind of form the foundation of what we're going to work on next, which will be, hopefully, C, plugging and playing different IFS solvers. So plug and play different IFS solvers, solvers for basically the fractal flame method. So I'm going to call it fflamify.jl. Now, here's where things get rather interesting and kind of complicated. In the discussions that we've had with the symbolic expression library and the fractal flame method, we kind of mentioned that we want to do general purpose GPU computation, right? And a lot of you guys have wondered, or maybe have seen, that we've been using the library Impero instead of the library Symbolics, where Impero was something that I created and a friend of mine created as a way to help with the Klima project, and Symbolics is a general purpose symbolic library for Julia. Now, here's the thing. Do we actually need Impero? The answer is probably not. We can probably get away with the symbolic library, but this is where things get rather complicated, and this is the heart of what I want to tackle today. How do we go from a symbolic expression library to valid GPU code? And that's what I'm hoping to kind of solve today. I don't know if we have a good solution for it, but we're gonna tackle it the best we can. Before getting into any of that, what I'm gonna do is go through a quick algorithm archive PR just to go ahead and get it down, and then hopefully we'll talk about the algorithm archive stuff a bit later as well. For today's schedule, I'm gonna be streaming from 1 o'clock p.m. to 6 o'clock p.m. Central European Standard Time. I actually don't know what time zone I'm on, but 1 to 6 p.m. CEST. This is just a time that I can manage today. Tomorrow, unfortunately, we have someone coming over to fix the washing machine and oven, so they're going to be here from 3 to 5, so I'm only going to be able to stream from 5 to maybe 8 p.m. CEST. But from there, I'm hoping to have somewhat regular working hours. We'll see if I can manage, but we'll just see what happens. But I'm hoping to have regular working hours from 12 to 8 p.m. CEST. This doesn't mean I'm going to be streaming that whole time. It just means that these are going to be the working hours that I'm dedicating to this project. I'm devoting all of the morning times to be kind of like just dealing with life stuff or dealing with other people's work and all this kind of stuff, so that I can dedicate the entire afternoon to specifically working on Leos Labs and really getting it off the ground in the next few weeks. Again, if you guys have any comments, questions, concerns, ideas, anything like that, feel free to let me know, and I'll totally address it as soon as I see it in chat. Again, like I said, the first thing we're going to do is go through an algorithm archive PR. So let's go to the algorithm archive. GitHub repository. I'm already messing up. Go to pull requests because I think there is a very quick one that we can do for this. I think that's a 1D convolution implementation in Python. Let me see. It looks like spacing code properly for readability. I think this is now done. So let me go ahead and pull this down locally and make sure it works. We're going to... by the way, Kenobyte... Oh, I cannot see because it's so far away. Let me see. Xenobyte off sec. I messed that up really, really badly. Thank you so much for the follow. Really appreciate it. Algorithm archive. And we're going to CD over here. Projects. Algorithm archive. Okay, so for those of you guys who may not have seen this... Wait. 1 second. Oh, I'm just now realizing I'm not getting any notifications in my Twitch. Hello. Oh. 1 second. My IRSSI setup seems to be wrong. That's why we're not getting any notifications. Let me try this again. IRSSI. Join. LAIOS Labs. Okay, hello? Did this work? For some reason, it's giving me a list of everyone who is... Okay, so I'm at least on now. All right, perfect. And let's go from there. Okay, great. Thanks for actually mentioning something in chat. I saw it over here on my side screen, and if I wouldn't have seen it on my side screen, I probably would not have even noticed that my chat was wrong. Also, I'm sorry, I didn't mean to, like, dox everyone here. Let me just go ahead and clear my screen. I don't know what's going to happen if people enter and leave the chat. There might be some weird IRC thing that like shows when people enter and leave. If that happens, I'm just going to modify my settings so that doesn't happen. I'm not sure how to set that IRSSI globally. Basically, ever since Twitch got hacked and I changed my name from Simuleos to Leos Labs, there have been a whole bunch of like weird things that have happened that have made it so it's difficult for me to like do the things I normally would. Like the IRSSI client just isn't working the way it's supposed to. Anyway. Doesn't matter. Let's go ahead and take a look at this PR. We're going to clear here. Take a look at git branch. Let's do git. Can I just pull it? Maybe because I'm already on the right branch. Oh, right. I was in the middle of something and I'm just completely scattered today. So, for those of you who may not have seen the algorithm archive before, it is, also called the Arcane Algorithm Archive. It is essentially a way for us to gather a bunch of algorithms that are relevant to the research that I'm doing, and relevant to everyone in overall, and basically give a good, concrete, clear description of what these algorithms are, along with implementations in various languages. So, for example, if we go to I don't know, the Euclidean algorithm here, we can actually switch between all of these different languages for the Euclidean algorithm, right? And the hope is that we can provide this for pretty much any language or any algorithm, right? So the PR that I'm looking at right now is convolutions in 1D for Python. We only have C# and Julia, and this PR will add a Python implementation. Okay, so let me go ahead and take a look at that PR really quick. I think I can just do view command line instructions, and I think I can just pull. Can I? What happens if I just do git pull? Is this going to work? Did it work? Git branch, git log. The latest thing is convolutional theorem implementation in Python, merge branch, 1D convolution. No, it didn't work. Okay, that's fine. Git checkout, master, git bod branch, git branch -d. Let's go ahead and remove this guy here. And then we're also going to remove this guy here. Actually, let's just remove a few of these guys since we're at it. There. This I think we can remove. And probably this one as well. All right, perfect. And let's go ahead and pull the command line instructions, bring it down, and check it out. Okay, so let's grab this guy. And basically, I just need to run the Python code to make sure it works appropriately. So we're going to cd into contents, convolutions, ls here, cd1d, ls cd python, or code, python, ls, and now we're going to do, what am I going to do? Python 1d convolution.py, ls here, and now let me just do head, come on, of cyclic.dat, and then back into the Julia directory, and then cyclic.dat. 503, 5.11, they're perfect, exactly what they're expected to be. Let's double check to make sure everything else is right. So we're going to do simple linear, and then /Julia, simple linear, 0.372, perfect. And the last one's going to be full linear as well. Full linear, and then /Julia, full linear, .dat. All right, they look good to me. I'm going to do a quick tail of this as well, just to make sure. But I think it's fine. Yeah, everything seems fine to me. Great, perfect. Okay, so the numbers are correct. I think we can go ahead and squash and merge this guy, and we're gonna do more PRs as we continue through today. I just kind of wanted to get one down on the books. Okay, so the code's producing. This is producing the correct output, and the code looks clean. I am happy to merge it. All right, let's go ahead and submit review. And give it a second. Squash and merge. Confirm squash and merge. Oh, I probably should have put the hackathon. Oh, Hacktoberfest accepted is on there. Perfect. Okay, so, you guys have noticed that I'm kind of treating maybe you guys haven't noticed, but I have been kind of treating the algorithm archive set of PRs as a stack rather than a queue, which means that people who are putting stuff out now are actually getting stuff done faster than people who put stuff in the queue like 2 years ago. The reason I'm not dealing with PRs from 2 years ago and I'm doing it this way is simply because the further we go back in history, the less likely it's going to be that people are actually going to respond to the PR. As much as that sucks, that's kind of where we are. We let a lot of PRs just kind of sit there, and quite frankly, because we couldn't get them reviewed, we just didn't know what to do with them. So yeah, we're in a really rough state with those. Anyway, let's go ahead and start moving on to the next bit of today's stream, journal, new page before, where we talk about how we go from a symbolic representation, we'll say equation, to a valid GPU kernel. So GPU kernel. Okay. There's actually a couple of different answers here. And actually, the overall question is somewhat vague. So let's start with the question of how do we get from point A to point B? What exactly is point A and what exactly is point B? So a symbolic when I'm saying a symbolic equation, I mean the following, like x squared plus 2. Okay. So this is our symbolic equation over. Let me try that again. X squared plus 2. Okay, let's make it a little bit bigger. Okay, maybe not that big. That's probably fine. Perfect. Okay, so when we say symbolic equations, we're talking about something like x squared plus 2, where x could be anything. Maybe it's an array of elements. Maybe it's a single number. It doesn't really matter. We don't really care at this level what x is. We just care about this representation. Now, a GPU kernel, on the other hand, is going to be, something specific, something that can run on a GPU. So let me just go ahead and grab one of those really quick. GitHub.com and just go to Simuleos and just pull one up. Simuleos, perfect. What is simple CC? Oh, simple closed captions, right. Let's go to GPU here, and then we can go to vectoradd.jl. Let's just get a simple one. Okay, I'm just gonna grab this kernel in here. Maybe I can turn this to, nah, it's fine, who cares? No one cares. All right, print screen, grab this guy. There, and we're just gonna move that over here. Where did it go? Screenshot, this one. So it should be the very last one that's done. This one here, bam. And move this down and over here. Okay, so we're specifically asking, how do we go from this to this? Now, for those of you guys who know Julia, you know that we can actually take use of the broadcasting infrastructure of Julia. All right, so let's go ahead and just discuss this, discuss this now before it gets out of hand. So we're going to CD into projects, Simuleos, and we're going to go into GPU. All right, we're going to do the same thing over here, CD projects, CD projects, Simuleos, and then GPU. I don't actually know if I have the appropriate performance testing mechanisms in here. So let me see. NV prof, great. Ncite. Do I have it? Ncite sys, probably. Come on. Okay, good. I have it. Wonderful. Hey, Emrys, how are you? I hope you're having a great day. So we're actually going to do a very quick, just, GPU benchmark, just to show you kind of where we're at, and why broadcasting isn't necessarily the best thing to do. Right. So also, it's been a while since I've done this, so forgive me if I'm a little bit rusty here. So we're going to run a couple of different things. So over here on the left, I'm actually going to have a screen up that's going to have, 1 second, NV top. Okay, so you can see the GPU memory and stuff as it kind of plays around. And then I'm going to have Julia right down here that we're going to be calling. Actually, no, I'll call Julia from over here so we can see it a bit better. And this will just be a random terminal for other things. Basically, just woke up. I love the fact that I have a day off from university. Wait, okay, actually, so today is actually a holiday in Barcelona and Spain as well. Apparently, there's like a big protest going on in one of the plazas in Spain. So we're kind of staying away from that. I don't really know. I think the protest is like about how people in Catalan, which is where Barcelona is, sometimes feel like they're Spanish and sometimes don't feel like they're Spanish, which is clearly a big problem because there's, an identity problem, all this kind of stuff. I don't fully understand why Hispanic Day is also on the same day as Christopher Columbus Day, or Indigenous Peoples Day or whatever. But that's neither here nor there. Okay, so here's what I'm going to do. I'm going to do Julia, and I think I have to do nsys launch Julia. And I think what I need to do next is run using CUDA. I'm just reminding myself of how to do this. Right. Nsys launch Julia 1.6. Right, nsys launch builds Julia 1. What do we have here? Dash 1.6.0 / bin Julia. There we go. Okay, so now we're going to do using CUDA. And what we should be able to do is just do a quick benchmark here. So I'm going to go ahead and create a couple arrays. A is going to be equal to Q array. 1 second. Q array of rand of 1000 by 1000. Something like that. And you should see the GPU memory on the upper left bump up in just a second as we're using some GPU memory. I think. I'm not really sure. Maybe it won't. And we're going to say B over here is going to be equal to another random array. Now what I'm going to do is say C is going to be equal similar of B, just to say it's just a Q array. And we're just going to say C is going to be dot equals to B dot plus A. Okay. So give me 1 second. Let this run. It's like compiling an addition and stuff. And then after this is done, I'm going to just benchmark this, which I think is going to be done with CUDA.atProfile. And then if I just close Julia, it should be good. Okay, so now we're going to run CUDA.atProfile. That command that I just did, C is going to be dot equal to A dot plus B. Give this a second. Processing events. Capturing symbolic files. Perfect. So for those of you guys who may be just not clear as to what I'm doing here, what I'm doing is I'm profiling the GPU code. One way to do that is with the ncite nsys commands. And what you see here is that we have a report1.qd.rep file output. So Control D. So the way this worked is I started Julia up, and then I started Julia with this nsys launch commands, which basically means we're going to capture the entire Julia runtime environment, I guess. And then what we do next is we run CUDA.atProfile on a specific command when we want to basically turn the profile on, do the profile, and then it turns off again once that command is done. So now that we have this done, we should be able to run nsys ncite I think just nsite sys should do it, and we should be able to run report1.qd-rep, and this should open up. Yes, here it is. Perfect. Okay, so this opens up the profiler for the code that we're running. All right, let's see. So here's what we're looking at here. So what we can do is we can actually, I think, just right click and show in events view. So we see here that we have kind of two things happening in the CUDA API. We have a Julia broadcast, and then we have a CUDA context synchronize, which is what you'd expect to see. So let me scroll in here, and let's just mess around a little bit. So I think if I go over here, you see here's the broadcast kernel. And essentially this is the a dot plus, or C is going to be dot equal to a dot plus B. So the broadcast operation is the thing that basically says each individual element of A and B are being added together, right? And here's that broadcast kernel. Now, note that this doesn't have anything. It doesn't have anything but the broadcast. It does have a lot but the broadcast, but what it doesn't have is the hardest part of the computation, or not hardest, but the longest part of the computation, which is the time it takes for you to copy data to the GPU. That's completely missing from this benchmark, and I can show you a benchmark in just a second where that comes into play, but quite frankly, it just completely overwhelms the broadcast kernel, so I didn't want to show it for this example. If you guys have questions as to like what we're looking at, or if I'm going through things too quickly, feel free to ask, and I'll answer it as soon as I see it in chat. This is one of those things that does, kind of sort of lend itself to being more in like a software engineering project than it does a science and tech project, but I don't really know. Like it doesn't really matter too much to me. Okay. So all of this stuff up here, all this black stuff up here, and this CUDA profiler thing over here, all of this is not the broadcast. So if I go here and we right click and we show an events viewer, all of this nonsense here, I mean, we do have the Julia broadcast kernel, but all of this is not GPU stuff. The only thing that the CUDA API actually called was this right here. Okay, let's go ahead and mess around a little bit more. So we were talking about how we want to turn a symbolic equation into a specific GPU kernel. And there's a reason we want to do that. And the reason is because even though we can use Julia's native broadcast infrastructure in order to do GPU computation, it doesn't make sense to do that a lot. And let me just kind of explain. So I'm going to go into Julia one more time. Nsys launch here. Perfect. I'm going to do using CUDA just like I did before. And the next thing I'm going to do is create a function, which is going to read in 3 values, and it's going to be vector add a lot. Okay, dumb function name, but don't worry about it. CAB. And in fact, just because it's Julia, let me just put an exclamation mark there. So we're going to say 4. Let me go back up here and add an N as well. N. For I is equal to 1 to N. C is going to be dot plus equals A dot plus B. Down here, we're going to end that, and here we're going to end that. So what I'm doing here is I'm putting all of those vector additions into a for loop, which basically means that, we're going to be calling the broadcast kernel again and again and again. We're going to create that function. And now what we're going to do is we're going to define A, B, and C again. So we're going to say A is going to be equal to Q array rand of 1,000, 1,000. We're going to say B is going to be Q array rand of 1,000, 1,000. And C is going to be C is going to be similar to B. We're going to run our function really quick, which is going to be V add a lot. It's going to be C, A, B, and we're going to do 10 for our iterations. So it's just adding C, A, and B 10 times. Then after this, I'm going to benchmark it. And I think you'll immediately see the problem once we do the benchmarking here. Cool. And also, guys, I do realize that this might be a bit esoteric for some people. Again, if you have any comments, questions, concerns, ideas, anything like that, just feel free to let me know. This type of stuff is not, like, as much as I want to say that all research scientists know how to do profiling and stuff like that, it's clear that a lot of people don't, right? And so if I say something that, doesn't make sense to you, just ask. I'm going to do my best to explain it. And sometimes maybe I don't know the answer, right? Like just because I've been doing GPU code and I've been using Julia for so long, doesn't mean I know everything, right? I'm going to reset C to be similar to B. And now we're going to say CUDA.appProfile v add a lot, 1 second, and we're gonna run maybe 100 times. Why not? So CAB, and then 100. Okay, give that a second. It's gonna profile everything and give us the results. So just before I left OIST, like when I was there last month or whatever, I decided, you know what I'm going to do? I'm here a month. I'm going to teach a mini course. They used to be called skill pills, but I don't think they're allowed to be called skill pills anymore for various reasons. The point is, I was like, I'm going to teach a mini course on how to run GPU code, right? And so I tried to run this very same example on the cluster that they had at OIST, and it just didn't work. And like there were so many times, I don't know what happened, but it just kept failing. It was this very same example that I'm showing to you right now. And it's super frustrating that here is working no problems, but for some reason at OIST it just wouldn't. Anyway, let's go ahead and run nsys, and I can't type, nsys, nsite sys, there we go, of report to .qdrep. Okay, so what we should see here, and let me just go ahead and take a look here, and let's go to the CUDA API, show an events viewer. We see here that we have a whole bunch of different broadcast kernels. Basically, there should be 100 of them. Yeah, well, 101 because there's a CUDA synchronize, but there are now 100 Julia broadcast kernels. So let's scroll in a little bit here. And this is exactly the problem with just relying on the Julia's native broadcasting infrastructure here. Now look, for the most part, if your broadcasting operation of a plus or a multiplier or whatever you're broadcasting takes a while because you have huge arrays, this doesn't matter so much. But the point is, as we scroll in here, okay, also note that the first broadcast kernel takes a while because of profiler overhead and stuff like that. But then if you go in here, look at the gaps between each broadcast. So here's a broadcast, there's a broadcast, there's a broadcast. All of this time in between each broadcast is essentially, I don't have a very good way of describing it, but it's essentially us going to the CPU and saying, hey man, we got to run another broadcast. So it basically runs another one and another one and another one. And these gaps are huge, right? Like in some sense, if we didn't have these gaps put together, the runtime of this would be way shorter, right? Almost a factor of 2, maybe even more, maybe even 3 shorter because of how big these gaps are in between. So I guess the next thing to do, just to kind of really drill this point home, would be to create a kernel that does the exact same thing, except it, which does the exact same thing, except that it does it all in one foul swoop, like one big kernel instead of a bunch of small broadcasts. Cool. Okay. But you guys are starting to see my point here, right? By relying on just symbolic equations and stuff like that, we can see x times x plus 2 as a bunch of broadcast operations. X plus x is just adding adding a and b together, and plus 2 is just adding 2 to that. So this would be 3 different broadcast operations. That's fine. That's not a big deal. This will totally work. But to really get that last little bit of performance, I think it is really necessary to convert this into a full GPU kernel. I think the question of, what we actually have to do with that is, that was a dumb question. The question of, how much performance we can actually get by doing this transformation is maybe not clear, right? So that's something else that we need to talk about as well. So that's on the docket of things to talk about. The first thing is I'm going to create the kernel and just do the benchmarking, the profiling of that kernel. So just like before, we're going to nsys launch Julia. And this time I'm going to create a CUDA kernel. So using CUDA, and this is where my knowledge of CUDA is starting to wane because I've completely forgotten how to write a basic CUDA kernel. Because it's changed a bit over the years. I know the @kernel syntax is for kernel abstractions. We have function kernel vadd. Let me just grab this guy. Okay, let me just don't judge me. Don't judge me. I'm hearing that judgment in chat, but I'm going to do this anyway. So kernel function vadd, and what I'm going to do is just put a for loop around this guy. How do you do that? Because I'm in the REPL, I'm actually not quite sure. So I think if I press enter here, yeah. So for I equals 1 to n, and here we're going to say abcn, but I'm going to change the notation so it's the same as last time. So cab n. And then we're going to do 1, 2, 3, 4. I need to go here, press enter, end, and then we're going to do end. So that should be our kernel v-add, and we'll launch it in just a second. Okay, let's go ahead and create A, B, and C again. So A is going to be coup array of 1000, 1000. B is going to be coup array of 1000, 1000, and C is going to be similar to B. We're going to go ahead and launch the kernel really quick, which can be done something like this. Is it correct to say that each time you iterate over the for loop, 100 CUDA threads are created and deleted? Okay, so CUDA threads... No. You're right to some extent. Actually, you're right, I think, in the heart of your argument is correct. But I think the way it was phrased may not be necessarily correct. Threads cannot be created nor... Well, you give threads work, right? So if you have a function, you disperse it against threads. At least from the terminology that I typically use, a thread is like a hardware thing, right? I don't usually use it to mean like a software thing. But the amount of work that you're giving to each thread is kind of created and destroyed each time. So in some sense, you're loading that thread with information, and you're having that thread process things and then coming back. So every time you're doing it, you're essentially relaunching and providing work again to those threads. So in some sense, you're right. In that you don't really have persistent memory between each broadcast. So you're completely right in the like idea of what you said. I just don't know if the terminology is exactly right. Okay. So we're going to actually just run this because I'm dumb. It's been a while since I've done anything with CUDA, so just forgive me here. 10, see if this actually runs. Error, DA not defined. That's because I just called them A, B, and C. And let's do it. So it's going to be C, A, B. This should run, I think. And then after that runs, we're good to go. So for those of you guys who don't know GPU kernels, essentially what we're doing is we're creating a set of blocks and threads here. Resolution not defined. Oh, right. The resolution is going to be 1024. I think I want the resolution to be 1000. So we're going to modify this so it just says 1000. Probably should have done 1024 now that I think about it, but it doesn't really matter. All right. See? Did it work? I don't think it worked. Let me take a look at the function here. Oh, that's because we don't have an I. Oh, wait, maybe we need to do a dot plus equals. Let's try that again. So let's do CUDA threads, and let's do C again. Okay, let's just define A and B to be 1024. I think I'm off by a factor. I think I need to do one more block. So div, and then we need to add one. Now let's try C. No, what? Okay, I actually don't know why this is broken. Sorry about that. Let me try making A and B a multiple of 1024. So A is going to be equal to coup-array of rand 1024, 1024. B is going to be 1024, 1024. And then C is going to be equal to similar of B. And now let's try it one more time. Now let's take a look at C. No, it made it worse. Okay, now I'm very interested to see what's happening here. So I'm going to say, what is happening here actually? I think I need to plot C to see which elements are actually being shown or are actually like being used and which ones are not being used. But right. Let me run this code really quick, just to make sure I'm not doing something wrong. There's nothing wrong with my Julia implementation here. So we're going to, we're in the right directory here. So let's just run Julia. Sorry, I have to run Julia 1.6. Now we're going to run include. We should just be able to vadd.jl, and this should give us test passed in the end. Give it a second to do all the pre-compilation instructions, and then we can go from there. I'm actually not entirely sure what I did wrong with the last one, so I'm going to just benchmark a single vector add, and then we're gonna go from there. Okay, so this did pass. So let me just mess around with it a bit. we should already have a kernel vadd available. So let's go ahead and do the same thing we did before. A is going to be equal to kuarray rand rand. B is going to be equal to kuarray rand rand. C is going to be equal to similar of that. Then we're going to do at CUDA. Let me just grab this exact same command and just see if it's actually running correctly. All right. At CUDA threads. Right, because I called them just A, B, and C. Okay. Resolution is not defined. Resolution should be 1024. Oh, you know what's happening here. No, I don't know what's happening. Actually, I thought I did, but now I'm actually confused. C. C is correct. What did I do? Okay. Yeah, okay, I don't know what I did, but I did something really dumb last time. Let me just try running this again and getting that profile for you guys. So we're going to do nsys launch. All right. I'm getting really paranoid now, but nsys launch. And now we're going to do using CUDA. Give it a second. We're going to define this kernel, and then we're going to define a new kernel. So we're going to define this kernel. Done. We're going to say resolution is going to be equal to 1024, just so I don't forget it. And then we're going to just make sure this kernel works. That's what we're going to do. So A is going to equal to kuarray. B is going to be equal to kuarray. C is going to be similar to B. And we literally just did this, and it worked just fine. So now we're going to say at CUDA threads 1024. Okay. Give me something. Come on. Whew. I'm actually quite nervous. Let me get a little bit of water. Why would this break? It's a simple vadd. Okay, so that's working just fine. So now we're going to do the same thing, except we're going to have a for loop in there. So we're going to say, where's our function? We're going to say kernel vadd a lot. And in here, we're going to add a for loop. Let me do that really quick. I think here. Oh. Oh, I got it. I'm an idiot. K equals 1 to n. I said for I equals 1 to n, but I is already defined as the block. So I think that's what happened. And then we're going to go down here and end in here. Okay, now we're going to call the same kernel we did before here, except we're going to say vadd a lot. Okay, give that a go. And then we'll redefine, oh no, don't give me that. That is because we did not have an n in the function call. It should be fine. And then we're going to go here and just say this is going to be 10. Okay, that seemed to have run. Let me run C. C has values completely filled. Perfect. So say C is going to be similar to B. Let's run this again with 100. And we're going to run CUDA.atProfile. And then hopefully this gives us what we want. Capturing the input and output. And then once that's done, we can take a look at that, at the benchmarking, and kind of compare the 100 different broadcasts versus the one big kernel. Now, of course, the kernel that we're working on is kind of it's a bit staged in that, you don't really write kernels the way in which we wrote that kernel, but we did it anyway. So we're going to run nsys, nsite, sys, and now we're going to run report3.qdrap. Okay, so here we should see, if we show an events viewer, basically just one Julia kernel, right? So let's go in here, and we see that one Julia kernel, I don't know, how long is this? It starts at 0.346 milliseconds, and it ends at 1.8 milliseconds. So this is going to be, 1.5 milliseconds total. If we look at report 2, and we scroll in here, we see that, right, so we said the last one was 1.5 milliseconds. This starts at about the same time, 1.3, and ends at basically 2.8, right? So we're talking about a difference of basically 1 millisecond between the two of them. Now, is 1 millisecond important? No, not really. Like, I realize that there's a bit of is it actually that important? Maybe not. Let me take a look at the CUDA overhead for report 3. Note that there still is a lot of profile overhead here that probably maybe even more overhead than in the single kernels. But the point is here, even in this very simple example, you can see a clear benefit of basically writing everything as a single kernel. Now, that benefit is kind of sort of outweighed by the fact that, like we just kind of did a really staged example here of having 100 vector broadcasts put together. By the way, Ikmog Donor, hey, how are you? I'm having a great day. So again, we had a very staged function that we were messing with here with 100 broadcasts versus a kernel with 100 with a for loop on the inside. Let's see, what do we think? Sorry for being irrelevant, but what do you think of COQ and Proof Assistant? I actually don't know much about it at all outside of a brief discussion I heard between Alex and Grant from 3 Blue and Brown, which may or may not have been in the 3 Blue and Brown podcast or not. If I understand this correctly, you're talking about proofs that can be computationally assisted in some way, in which case I think it's fine. I actually don't fully understand the problem with it, but I would be more than happy for you to tell me what the problem is in chat. Because clearly it's something that people are very passionate about and something that people care a lot about, but I don't fully understand what the problem is by allowing proofs to be computationally assisted. I don't fully understand it. And maybe I'm thinking about something different also. So sorry, I don't have a really good answer for you. Okay, so what did we see here? Just to be clear and to write things down, we showed that if we do 100 broadcasts, versus one kernel with 100 adds, we saw that this one was 1.5 milliseconds, whereas this one over here was 2.5 milliseconds, roughly. I mean, look, it's not exact, but roughly something like that. So we're seeing a 100 millisecond improvement in this very simple case, right? Now, like I said before, we need to take this with a grain of salt because this is very manufactured. Under what situation are you going to have a symbolic equation with 100 things to work with, right? So here we see a symbolic equation of x squared plus 2. Well, that's just 3, right? And, the difference between 3 broadcasts and one kernel with 3 adds, let's say broadcasts, it's nowhere near as big as the change here, right? So, and also the fact is we're working with very small numbers here, or small amounts of numbers. So, the computation isn't really that big to really warrant this type of level of criticism, right? So what I'm trying to ask is the following. If we have a symbolic set of equations, right? So let's say we have f is equal to p plus a over 2. F1 is equal to p plus b over 2. F3 is equal to p plus c over 2, right? And then we have, the Barnsley-Fern ones, so G1, G2, G3, G4. Essentially what I'm saying is we have a bunch of different equations that we're trying to solve here. So this guy right here is what? 3, 3, 3. Each of these guys is going to be an affine transformation plus a linear transformation. So you can get those down to probably 3, 3, 3 as well. And the point is, as we start adding more and more equations to the set of equations that we're trying to solve for our iterated function system, we do kind of sort of get to the point where maybe we have potentially 100 broadcasts to deal with, right? So my naive question here is it okay just to keep things in symbolic form, or should we find a way to transpile that into a GPU kernel? That's my question. I don't know if my gut instinct is that we should definitely transform it into a GPU kernel. But that's hard. And we already have the symbolic representation that probably works on GPU arrays just fine. So if we just want to broadcast, maybe that's fine. This is, in fact, why we had created Impero versus just using the symbolic utilities already available in Julia. Because with Impero, we can kind of figure out how to do this step on our own. Whereas with the symbolic utilities, it's a bit harder, right? All right, let me get a little bit of water. And let's just think about what's actually necessary to go from where we are right now, which is, a rough symbolic library, to where we want to be, where everything is compiled on the GPU. Mm. And not only the GPU. In fact, we want to use a library known as Kernel Abstractions, Kernel Abstractions, which will basically allow us to write one code base that works both on the CPU and GPU. COQ isn't exactly automated theorem proving. It's mainly about written mathematical proofs and making sure that what you wrote is correct. Oh yeah, then in that case, 100%. If it's just checking to make sure that your proofs are correct, I'm a big fan of that. I think, yeah, let's do it. Like, let's just, have a way to automate that process. I'll take a look at that in just a second. What hardware am I currently running on? Right now, my desktop PC is a very simple GPU, literally a really old one, GTX 970. I need to upgrade, but I haven't. And then a Ryzen 3700X or whatever. But I work a lot with high performance computers. So this means that I do a lot of stuff on supercomputers, and that means that I have, very high end, stuff to work on, right? So essentially everything that I'm doing on my desktop is more or less just testing for when it's eventually on a supercomputer, right? So that means a lot of GPUs, a lot of CPUs and stuff like that. And actually with that topic of having a lot of CPUs and having a lot of GPUs, we also need to consider, distributed effects here. So like, how easy is it to do x squared plus 2 if x is bigger than what can fit on a single GPU? Stuff like that. Also, COQ is pronounced coq since it's French. Oh, okay, fair enough. Never knew that. In fact, I'd only heard about it now, so it'd be surprising if I did know that. Let's take a look over here. Open this up, paste there, and see what we got. Also, I'm going to remove the profiling here. Natural number game version 1.33. Oh, this is interesting. Okay. Yeah, okay. Yeah. I don't know what this is exactly. Welcome to the natural number game, a part book, part game, which shows the power of induction. Let's see. Gray nodes you should stay away from. Wait. Blue nodes on the graph are ones that you're ready to enter. Gray nodes you should stay away from. A gray node turns blue when all nodes above it are complete. Green nodes are completed. Okay. In this game, you'll get your own version of natural numbers called MyNat in an interactive theorem prover called Lean. Okay, so click here. Okay. I mean, I'm not going to go through this on stream, but it's quite cool. Declaration MyNat uses sorry. All right. I don't know what any of this is, but I think it's quite cool. Again, if you're asking me, like if anyone asks me, should I automate this process? My answer is almost always yes, because I always feel like automating something is better than not having it automated. Okay. I've been streaming for about 52 minutes now, and I haven't yet mentioned this. Okay, here's the thing. I'm trying to make it so people do more research on Twitch, and one way to get people to do more research, how am I missing the H every single time I do that? HTTPS. I don't understand. Anyway, the point is, yeah, I don't understand it. I'm trying to get more people to do research on Twitch. I don't know exactly the best way to do that, but I feel like one way to do that is to at least provide people a way in which they can do research on Twitch and know that people can at least find their stream, right? Because right now, if you're trying to find my stream, you can find it on Science and Tech. Maybe at some point I might be streaming on software and game development. I'm not really sure. But what would be super nice is if I could just say, hey, I'm looking for people who are doing physics research or chemistry research or whatever, and I could just click on the research tag. And so that's what I'm thinking. If we could make this research tag a thing, I'd be super happy. I don't think it's going to happen. I mean, look, we only have 21 people who have voted on it so far, and no matter what I do, I can't get people interested in this. I mean, for me personally, and I've mentioned this before, I genuinely feel like, the biggest problems facing today's society have nothing to do with, climate change. They have nothing to do, well, okay, they have a lot to do with that. The biggest problems facing today's society, climate change, anti-vaccine people, all this kind of stuff, comes from a stem, or it comes from a seed of anti-intellectualism that just kind of is, breeding in society. And what we need to do is make it so it's harder for them to keep festering, So the easiest way to do that, I feel, is to really show what research is like in a public, open way, which is why I'm doing the stream here. and I'm talking about it live, and I'm really trying to get more people involved. So we'll just see how it goes. Anyway, I just want to mention, if you haven't, please feel free to vote on this. I'd really appreciate that. The natural number game basically takes you on a journey proving properties about natural numbers and operations by starting from Peano's axioms. I thought it was very fun and got me very interested in this stuff. Yeah, I'm super happy to hear that. Anytime I see that type of interactive stuff, I'm happy with that. Keeping multiple GPUs in sync and distribute the work is hard. I had a horrible time getting 12 1080 Ti's in sync, and also had to handle errors like power loss in half the cluster or hardware failure and rebalance the work. Right, exactly. This is why anytime people argue with me, okay, I don't get too many people arguing with me, but a lot of people tell me that, research software engineering is not interesting. And to some extent, I understand what they're saying, right? Like, if you're doing research software engineering, quite frankly, you're probably not publishing papers that are, pushing the boundary of human knowledge and all this kind of stuff. But it's hard work. Like, it's a lot of work, making sure that all of the code's up to date, making sure it actually runs on all the hardware. Like, it takes, the foundation of modern research is software. And, we need to pay respect to people who are writing that software. But, that's just not how it's done nowadays. So, when you start talking to me about like distributed GPUs, I mean, you're preaching to the choir. I totally agree. I had to do similar things before, both at OIST and at MIT, and it's just a lot of work that kind of goes uncredited. Maybe in industry it's credited more, but at least in academia, people just kind of see it as, the least interesting part of the project, or the thing they're waiting on so they can get the results out, and it's just a bit frustrating, Okay. So we're going to take a second and we're going to think about what we need to do to go from our symbolic equations to a GPU kernel using kernel abstractions. So to do this, the first thing I'm going to do is actually open up the symbolics toolkit in Julia and just kind of mess around with it a bit. We had been using Impero, and Impero allows for us to have these systems of equations that can then be almost directly, the hope was that these would be able to be transpiled into GPU code. That's kind of what we're looking to be able to do. Now, I actually don't know the best way to do this. It could be part of a two-step process where, users will write down the code or write down the equations they want to solve, and this is transpiled and then that's run. But I feel like there's some trick in the Julia's compilation process. In fact, I know there's a trick because I've seen it done before, where you can take code that is already existing and basically turn it into code that the compiler can actually understand, right? This is done via chotomate sumimasen kernel abstractions .jl. What is it? Is it still even used in the source code here? I don't know anymore. Let's take a look at compiler.jl. Struct compiler metadata. Overdub cassette. That's what I'm looking for, cassette. So what it allows you to do is take code that exists, that you've written, and overdub it with something that will work. So the idea would be that we would write the symbolic code that we want, and then potentially we'd use cassette to rewrite it into a valid GPU or CPU code, using kernel abstractions as kind of a base here, as something to work with, right? Now, I'm a bit sketched out doing this because I know cassette's kind of a pain to use. So I don't actually know if this is the right direction, but it is a direction that I think we could go in. Before doing that, though, give me just 1 minute. I'll be right back, and then we'll kind of start talking about this a bit more. So give me a second. Okay, back. Give me just 1 minute, and then I'll put my face back up. Right, for some reason my internet kind of was spotty for a second there. I don't think I lost any frames. It doesn't say I lost any frames. I don't think. No, it says no drop frames. So it should be fine, but my internet on my laptop was kind of a bit finicky. I don't know if that meant the Wi-Fi was a bit finicky or not, but it seems fine. Okay, let's go back over here, and let's go from here. Oh, actually, I should have been over here. There. Okay. So, what are the strategies that I'm thinking about doing right now? So, journal, new page before. Again, we're trying to go from symbolic equations to valid GPU code. Again, easiest way to do this is with broadcasting. This will work. It's fine. It's totally fine to do this. We're just being kind of a bit persnickety here by saying that, probably we want to rewrite it as GPU code. So the next thing we want to consider here is potentially using cassette to overdub the equations that we have with valid GPU code. So that's another thing that we could consider. Now, the third thing, or something else that we could consider here, is somehow incorporating the equations into, incorporating, building, I don't know how to put this. That's not how you put it. Oh, 1 second. Building the equations into pre-existing GPU kernels. So the idea here would be that we have the kernels kind of like the husk of the kernels available, and then we would kind of put the equations in to kernels that already exist. So we kind of pass the symbolic expression into those kernels. Again, like I said before, we are being a bit, not necessarily over-optimizing, but we're being a bit persnickety here. The cassette to overdub, I think, is also maybe a bit overkill. I think there is a way for us to just read in the symbolic expression that we want to solve into a kernel and have that be solved, but I'm not entirely sure about that either. So let me get some water. I feel like there must be. It must be fine. So I'm going to go ahead and mess around with this. I'm actually going to do that part first. So let's go ahead and do the symbolic library. Mess around with that, just symbolics.jl. See if I can get something basic, just a very basic equation working. First using broadcasting, and then I'm going to try to do the same thing. Via just putting that into a GPU kernel and see what happens. What's the worst that could happen, right? So we're going to do Julia 1.6. There we go. And now we're going to do add symbolics. Give it a second to build, and we're just going to mess around with it. This is not too different than Impero, which we were working on last time, so it should basically work the same. For our purposes, honestly, Impero is probably fine. It's just that I wanted to mess around with symbolics today since we were messing around with Impero so much the other day. Oh man, there's a lot here. Actually, I see that it's already building CUDA, which is interesting. So maybe they already have a way to do this already. So let's look at symbolics. Julia, and let's see what we got here. Julia symbolics, let me do symbolics.jl, and let's see if we can find anything for GPU here. Comparison against SymPy, nope. Okay, let's see if we can find CUDA. Maybe Kernel Abstractions. Supported type and dispatch symbolics. Okay, let's see what we have here. Kernel, nope. Okay, so where's Kernel Abstractions? It said it was on this page. Supported types and dispatch in symbolics. There is a tension between types as a representation of expression trees and types that are subtypes of... Wait, let me reread this. I'm sorry. There is a tension between types as representations of expression trees and types that are subtypes of types already present in Julia. We want to be able to deal with expression trees in a unified way and not constrain expression trees themselves to be under an abstract type in Julia's type hierarchy. For example, if we said that all expression trees are subtypes of real, then we couldn't represent array operations using the same expression tree. But we also want to be able to pass in expression trees into places in existing code that accept real values. We accomplish this by wrapping expression trees in a simple wrapper type, which is a subtype of our desired abstract type. For example, we wrap expression trees in the type num, which is subtype of real, to make it behave like a real number. Okay, so user-facing APIs and symbolics always take wrapped objects like num. They are then internally unwrapped for expression tree manipulation. So due to it requiring such wrappers, we only fully support a limited number of types, as both the type of expression trees and the type as Julia sees them. This is somewhat a type of confusing article is what this is. So real numbers, complex numbers, and arrays of real and complex numbers are the only ones that they support. Now, is this okay? Let me think. I think it is okay for our purposes here. I don't think that it's going to be too complicated. So what I'm going to try is I'm going to try to create a variable, and I'm going to try to just put that into a kernel and see if this works. I'm almost 100% sure it's not going to just work. There's going to be some sort of sticky tape that I have to put in there to make it work. But I would love to be able to just pass in an equation and have it be solved on the GPU. That'd be great if we could do that. Don't know if we can, but it'd be great if we could. Okay. So this means we have to do a few things. First, let's just mess around with symbolics library. All right, and see what we can do. And first, I'm just going to double check that broadcasts work. I think they do. I think if we just have GPU arrays, we can just use them. But let's see. I'm almost positive they work in Impero, which is great. I don't know if they work in symbolics. So let's just see what we can do. So I'm going to say A is going to be equal to rand of... Actually, how do I want to do this? I'm going to add variables A, B, C. Okay, so now I should be able to do C equals A plus B. Okay, so it doesn't see equals as a symbolic thing, which is fine. I wish it did, but it doesn't. So that's also not a problem. So we have A plus B as our symbolic representation here. So now let's see what happens if we eval. So let's say A is equal to 1, B is equal to 1, and now we eval A plus B. Oh, that's not going to work, is it? A, type of A. So let's do add variables, A and B. So now let's do A is just A. So now if I do, 1 second, I have to think about this. Let me just go to the manual here. Variable and equation types. Or is there a tutorial? Symbolic calculations and building callable functions. Sure, maybe. X squared plus Y, add variables. Z is an expression tree for square X and add Y. Right? So using LaTeXify, okay, I don't need that. Using sparse arrays, again, not interested in that. Derivative, simplification, and substitution. Okay. But how do I evaluate? That's my question. So what if I do the following? What if I do C is equal to A plus B again? Then we say A is equal to 1, B is equal to 1, and now we say C is A plus B. So C is the expression tree of A plus B, which is fine. And then what I want to do is just evaluate C. So can I just do eval C? No. Maybe evaluating the expression. Eval. High-level differentiation function, symbolic calculations, building callable functions. Okay, well this is the same one I was just on. Maybe it's at the bottom. No. Okay. Call. Okay, call build function. So this generates some code, which doesn't help me. Let's unpack what it's doing using a.nz value. So, okay, I'm being a bit persnickety here. I need to be a bit more relaxed about this. But it is a bit weird to me that we don't have a simple just like, here's A plus B in the tutorials, right? Am I the only one that would have thought of that? Okay, so tutorials here, home. Okay, using package, citation, feature summary, extension packages. Okay, symbolic calculations build in callable functions. We have variables x, y, x squared plus y. Again, this is fine. I just want to evaluate an expression tree. Let's see if I can just find it. Evaluating expression tree symbolics. Julia. See what we can find. Again, guys, if you have any comments, questions, concerns, ideas, anything like that, feel free to let me know. The chat's a bit quiet, which is, it's fine. It's just always a bit disconcerting. Okay. Let's go here, make sure I spelled Julia correctly, then let's look it up in Google instead of DuckDuckGo, because quite frankly, I never get what I need in DuckDuckGo anyway. Advanced expression manipulation. I feel like we don't need... Anyway, fine. Wait, what's Julia Hub? Wait, why are we using SymPy? In Julia, using SymPy. Yeah, okay, but no, I want to... If I substitute in x and y, if I say what x and y are, I should be able to evaluate what they are. I didn't realize that SymPy was something in Julia, actually. In Julia, 1 plus x, that's all fine. How do we... Come on, just give me a simple evaluation function. Anything here. Anything at all. Evaluate. Maybe if I just look for evaluate. All right. I mean, I know I don't know what the term is that I'm supposed to be looking for here. Prevent expression eval f. To evaluate a numerical expression into floating point number, use eval f. Okay. So eval. See. Dang. I really thought. Okay. So let's do symbolics. Dot symbolics dot. Let's see what we can find here. I really thought it would be evaluate, but it doesn't seem to be. So let me see what else we have here. An AC rule, that's all stuff for symbolic expressions or symbolic utils. Target function. Rule set build, maybe is what I'm looking for. Eval, I really thought it was eval, but it doesn't seem to do what I want it to do. Expressions occur in get variables, get name, include is idx, minor, termify, symbolics, supremum, supremum. I actually don't know what that word means. I forgot. I think it's like, well, no, it's not maximum. Supremum. What is supremum? Termify. What's termify do? Unwrap, evaluate. Okay, maybe I just use Impero because at least I know how to use Impero. Maybe that's the actual answer here. I mean, I get that. I get that we have this symbolic expression. My question is, how do I plug a number into that? C. Let me just do dump. C. Right. Okay. That doesn't. That's. I guess I should have expected that, right? We have the immutable dictionary, which is a symbolic expression wrapper. Okay, I'm spending too long on this. Let me spend another maybe 20 minutes on this. If I can't go anywhere, then I'm going to take a step back and just use Impero for this, and then I'll try to figure out how to do it in symbolic utils later. But right now, I'm really struggling at figuring out how to do this in symbolics.jl. Again, this has nothing to do with symbolics. It just has to do with the fact that I don't know this library very well. So there's SymPy, and let's go back to symbolics and see if we just have evaluate. Symbolics.build function, maybe. Let me see what we have here. Comparisons against SymPy. Performance build function. Limit is fine for some people, but if you're building a super fast MPI-enabled Julia C4 simulation code, having a function that hits the Python interpreter less than optimal. Sure. Symbolics.jl. Just give it to me. Just give me. How do you build function? Is that what I'm looking for? Build. Build function C. Nope. What is this? Okay, so the truth is a lot of times when it comes to Julia packages, you kind of get the same like feeling here. Like it almost always feels like you're just banging your head against the wall trying to figure it out because the documentation kind of always lets you down. So this is par for the course. I do understand that, but just evaluating 1 plus 1 is all I'm looking for. Just how do you evaluate 1 plus 1? Once I can do that, everything else is easy. Variables x, y, z is equal to x plus y. A is going to be this thing, fine. So if I don't care about LaTeXify, that's fine. Sparse arrays, okay. Function fu. Variables u, derivatives t, variable t, d is differential of t. Again, don't need that right now. Simplification and substitution. Non-interactive development. Building functions. It must be this part, right? To compute. So we build function to compute. So what's to compute? So we function expression. What is this? Function or building functions? The function for building functions from symbolic expressions is the aptly named build function. Okay, well, like everyone else uses evaluate, so like why are you calling it something different? The first argument is a symbolic expression or the array of symbolic expressions to compile. And the trailing arguments are the arguments of the function. So for example, to compute is going to be that guy. Sure. And then we have x, y. So do I just do build function c and then do a, b? Okay. Okay, so this gives back two codes. The first is a function f of x, y that computes and builds the output vector. That builds an output vector x squared plus y squared, because this tool was made to be used for all the cool kids writing fast Julia codes. It's specialized to Julia and supports features like static arrays, for example. Okay, the second function is an in-place non-allocating mutating function which mutates the first value. We use it like the following. My function f is to evaluate f of expression 2. Now what is f of expression? F expression 1, f expression 2. Okay, we're just gonna do this then. Like fine, screw it. This is what we're gonna do. Let's go over here and let's just mess around then. I'm gonna open up a new thing. I'm just gonna make it small, put it over here. And we're just going to look at that exact page and try to replicate it in Julia. All right, go here, paste. There we go. Okay, so let's just do it. To compute, here. Error. Okay, add variables, x, y. All right, now x, y. All right, maybe. To compute there. All right, seems fine. Then we have x expression as build expression here. This gives us two different things. F of 1, f expression of 1 is what? Okay, of 2 is what? Okay. At inbounds begin. Okay, I see what this is trying to do. It's trying to create a function that we can do exactly what we said before. It's creating a function that we can just plug in to a kernel, I think, or something like that, I think. So let's keep messing, because I think if we keep pushing, we can actually get this to work. So what do we have here? We have using static arrays, my function is to evaluate f of expression 1. So, okay, let's just do it. This should... Okay, let's go ahead and add using static arrays. So add static arrays, and let's try it one more time. Let me get some water. It's been a very long time since I had to deal with static arrays. I feel like I should have been dealing with them a lot for the past few months, but I just haven't. Okay, so now we're going to do using static arrays. All right. We're going to do my f here. Okay, well, it evaluates. What's 2? Sorry. So we have my function here. So what happens if we do my f here? Okay, that's an error because I don't know what 2 is. So this gives back 2 codes. The first is a function f of x, y that computes and builds the output vector x squared plus y squared plus x. Okay, so what is f of 2? The second function is an in-place non-allocating mutating function, which mutates the first value. Okay, so essentially what we're doing here is we're returning back 2 different functions, one that mutates the first variable, the other that doesn't. Fair enough. Okay, so thus we'd like to use the following. So, okay, fair enough. So this is the mutating one, and this should be fine. And then we mutate it out. Yes, we mutated out. So the difference here is that one is mutating variables, the other is non-mutating. That's the difference, which is fine. Like, that's totally fine. So then we write function.jl string f. To save the symbolic calculation for later, we take this expression and save it to a file. Okay, so it seems to me like we basically created 2 functions, and we could potentially pass one of those functions into a kernel, maybe? So let's see what we can do. So build function to compute x, y, expressions, val, yeah, okay. So in principle, this will work. So let's go ahead and mess around with it a bit more. We're going to do control D, L is here, and we're just going to create a new, let me go ahead and remove qdrdps star.qdrep files. Okay, L is here. Now we're going to create a new file, which is going to be called symbolic test.jl. Okay, so here we're going to do using symbolics. All right, using... Let's do kernel abstractions so we can test to see if it works on CPU and GPU. I don't know why I'm capitalizing these. So using symbolics, using kernel abstractions. All right, it's been a while since I did kernel abstraction, so I'm just going to do a simple vector add, essentially. So let's just see how that goes. So what I'm going to try to do is I'm going to try to create a symbolic expression that is literally just x plus y, put that into the kernel that we're evaluating, and go from there. So I think we do at kernel function, what, 2 arguments? I mean, what are we actually going to do here? We're going to call it symbolic test. Symbolic test kernel. We want to CAB, something like this, I guess. And is this okay if we do it this way? Okay, let's think about this later. So the reason I'm asking if this is okay is because in the end, we basically want to find a way to evaluate functions on GPU kernels, but we might not know all the function arguments. So, okay, well, the other thing that we want to read in here is actually the function itself. So we're going to read in the function f. I am going to be very skeptical. Okay, we know that the last kernel for vector addition worked in 1.5 milliseconds. I should not have deleted the qdrep file, but I did already. So we're just going to see how long this kernel takes to run. It's probably going to be slower than just the broadcasting methods, but you know, we can talk about that after it's done. So we read in f. Let me just... let me open up some code over here as well. So we're going to go into VI, vadd, okay, ls here, vi vecadd, dot jl, and I believe there's a kernel abstractions version. There does not seem to be. Oh, there it is, vadd ka. Okay, so let's just kind of follow this. I'm sorry, I'm like really quite tired right now, and I'm not remembering any of the syntax. So I'm using this as a way to jog my memory a bit. So a comma j is going to be equal to at index, and then it should be global of n tuple. Now I don't actually remember. I guess because it's returning an n tuple. Okay. Now here's where I just want to evaluate f, and so I should be able to just put f of CAB. And that should work if we're reading in a function. I don't know. We're going to try this really quick. So let's just try a simple... Let's see what happens. I don't know if this is going to work or not. I think it will work on the CPU, but I'm not sure if it will work on the GPU or not. Okay. So let's go down here. And so for those of you who may not have seen kernel abstractions before, it's essentially a way for you to write a single piece of code that executes on both the CPU and GPU. The way it typically works is you write your kernel, which is this guy up here, and then you write some way to dispatch onto the CPU and GPU, and that's what we're going to write next. So this is going to be function, and we're going to call it symbolic test. This is going to read in A, B, and C, and F. A, B, C, and F. And here, for the sake of the argument, we're going to just say if is a array, if A is an array, and here, and we're going to put an else statement in here, and then basically what we're going to say is we're going to run, we're going to say that our kernel that we're going to be running is going to be equal to symbolic test kernel, exclamation mark, executing on the CPU, and I think we want to use 4 threads or something. Now we're going to do the same thing down here, except we're going to say it's going to run on the CUDA device. 1 second. There, CUDA device, capital D. And we're going to say it uses 256 threads. All right, DD here. Okay, what's next? So next what we have to do is just execute the kernel. Kernel on A, B, C, and F with something called an ND range, which is like your like the size of your array and stuff. So ND range is equal to size of C. Is going to be equal to size of C. Okay. David Knight Soul, thank you so much for following. Really appreciate it. Okay. So, I guess we're just going to do it then, right? Again, this is going to be a simple vector add test. To some extent, I'm wondering how extensible this is to different functions and stuff like that, but we'll get to that, I guess. So let's go and say at test set, and I guess I'm going to do using tests up here. And then probably also using CUDA. I think that's everything I need. So let's go down here at test set, and we're going to say CPU and GPU kernels. Again, we're just kind of following the other code. And then we're going to say begin. And here, for those of you guys who may be new to Julia, the reason we're actually wrapping it in a test set rather than just leaving it all in the global scope is 1, so we can do the testing, but 2, Julia just does better when everything's kind of appropriately scoped. When things are in the global scope, it kind of runs things line by line instead of like function by function, whereas if you put in a test set, it kind of compiles that all as one big thing instead of a bunch of separate line by line interactions. Okay. So in here, I'm going to do A is going to be equal to rand of 256, 256. All right. B is going to be equal to rand of 256, 256. Okay. And then C is going to be equal to zeros of 256, 256. Now, what we're going to say is we're going to create an event, and I'm going to fill in the in-between in just a second, is going to be equal to symbolic test here of A, B, C, and I'm going to create F in just a second. And then once the event is done, we're going to wait for that, for event, and we're going to say at test is approx of C, and then A plus B. We're just testing to make sure this actually did what we expect it to do. Okay, so now let's go ahead and try to create the kernel for our symbolic test here. This is where things are going to get a bit funky. I'm not sure where I should define F. I want to put it at the top here, maybe. Okay, so we're going to do at variables, I guess A, B, C, right? And now we're going to say F is going to be equal to A, C is going to be equal to A plus B. All right, now let's see if we can figure this guy out. So what they did before is they said that, wait 1 second. They have building functions, so they do to compute. So we have an expression here, and then we build the function to compute. Okay. So let's go ahead and do that then. So we're going to do C is equal to A plus B. And actually maybe running, like maybe we don't need F. Let's think about that really quick. So now we're going to do f is going to be equal to build function. Oh, actually, maybe we need to do it dd d3d paste. Maybe we have to do it under here. So we do f is going to be equal to build function of the function that we're going to be computing. So this is going to be c, and it's going to take in the variables a and b. Okay, that seems fine. And it also says to me that we don't actually need... Oh, no, I think this is fine. Okay, so we create f, which is going to be c equals a plus b. And we want to read that function in to see if it actually computes on the CPU. Look, this is super sketchy. If this works, I'm going to be amazed. So now this creates two functions, and we want to grab the second one, because the second one is going to be the one that mutates the variables. And let's see what we got here. So let me go down here. And so we have my function is going to be evaluate function 2. So we created the function here. So my function is equal to evaluate f of expression 2. Out is going to be zeros of 2. So then we run my function out. Okay, so now what we want to do is run this on eval f of 2. Or maybe I should do it the following way. Maybe this should just be f, just so we don't get confusing. And then here we do eval a build function of 2, something like that. Yeah, it's still messy, but whatever. We'll keep working on that. DM6423, thank you so much for following. Really appreciate it. Hope you're all having a wonderful day. Again, chat's quite quiet today, but if you guys have any comments, questions, concerns, anything like that, just let me know, and I'll do what I can to answer it as soon as I see it. Not sure why chat's so quiet, but it's okay. Some days are like this. It's not a big deal. Okay. So we have build function, and we should be able to pass that in. I don't know exactly what eval does in this case, so we need to think about that. But I think what this did is I think it pulled the function out that we can now call, and we've evaluated with the numbers in there. Let's see what we get. We're all sleepy, I guess. That's probably fine. Again, it's really not a huge deal at all. It's just that it's been like 30 minutes since the last chat, or actually 40 minutes since the last person said anyone in chat, which is super long. You know, it's just been a while, so I thought maybe there was something wrong with the stream or something, but it's cool. I mean, if you guys are doing okay, then there's absolutely no problems. Okay, so we have f, we have evaluate. This is not going to compile. There's no way this is going to compile. All right, we're just going to run Julia, and we're going to do include symbolic tests or something. Sure. You having a sleepy morning? Oh, that's fair. I actually don't. I mean, it's what, 2:30 in the afternoon, my time. I'm going to be streaming until about 6, I think. So we have another 3 hours and 30 minutes. Really, if we can get this symbolic test thing to work, I mean, that's really good. Like, we made some significant progress today. I'm happy with that. And then we can think about what we need to do from there. What package are you using right here? So right now I'm using symbolics. Oh, well, the packages are up here. So it's Kernel Abstractions, Test, Symbolics, and CUDA. And the hope is that I can just read in the equation x plus y into the kernel and have it compute. I'm then going to take a step back and try to do this on the GPU as well. I'm testing only the CPU version right now. Import package. I don't have kernel abstractions? Oh, I know what I did. I need to run Julia 1.6. And now we should be able to just run everything. There's no way I don't have kernel abstractions, right? That'd be super embarrassing. Let me get some water. Yeah, so for those who may not know what the packages do, the first package is symbolics. This is the symbolic utility, so like x plus x. That is a symbolic equation, and it's just how we represent it. So it's this at variables and the c plus a plus b, and f is equal to evaluate and stuff. Kernel abstractions. Ooh, okay, let's try that again. I don't have kernel abstractions. Add kernel abstractions is what allows for us to do heterogeneous computing. So that's computing, like writing a single kernel, so this stuff up here, that executes on both the CPU and GPU. Test just allows us to do a test set and just run a test. And CUDA is the backend that we're using for the GPU. So that's what we're doing. Why is it compiling plots for kernel abstractions? Anyway, give it a second. It's probably fine. I don't know what's happening anymore. Let me check my notifications really quick. Sorry. Every once in a while, Streamlabs just doesn't work for me, so I have to check it out. I guess it's working fine. Okay, so that is built. Let's try it one more time. Include kernel abstractions. Again, I'm expecting this to break. I'm expecting that we're going to have to mess around with things a bit after this. So don't fret if we get an error. You know, like, this is just going to take some time to mess around with. Right, perfect. Error, wonderful. What is the error? So error during test. Got exception outside of @test. No method matching. Get index of expression. Int 64. Okay, this is good. Let's mess around with it some more. So we're going to do Julia over here, and we're going to do using symbolics. And we're just going to mess around. We're going to see what we can do. So what it's saying right now is that there is no function for indexing within a... Okay, I think I see what's happening. I need to think about this a bit more. But basically it's saying we cannot index into an expression, which is true. And this is kind of what I expected the error to be. But again, let's just mess around a little bit more. Man, I'm so sorry. I'm doing something wrong today, and I don't know what I'm doing that's wrong. Okay, let's go here and go over here and just kind of mess around. So I'm going to go ahead and create the f expressions like they did up here. To expression compute here. X not defined, right? Okay. X, sorry. At variables, Okay, X, Y. Okay, so now we do to compute, and we're going to create f expression. Okay, and yeah, so this creates two different expressions, one that returns, one that doesn't return. And we're just going to go down here and say this, my function is equal to evaluate f of expression 2. So now I want to check the type of my f. Type of my f function here. My f? What does this do? So, I need to think really quick. So it's saying the type of my f is just var of number 1, number 2, which is that how functions work in Julia? So function check, and we're just gonna say ab. Ab. Return a plus b. And actually, no. Let's just say a is equal. Let's make it mutable, so it's the same. A b. A is going to be dot. Plus equals b. End. All right, there we go. So what am I going to do next? I'm going to do type of check. Check exclamation mark. That wasn't what I was expecting. Type of check returns type of check? No, that doesn't make any sense to me. What if we do type of add? Add. Fine. Any function, doesn't matter. Add in. I don't think this is right. I think that's how anonymous functions usually return their type, but I could be wrong. Oh, yeah, you're probably right. It's probably an anonymous function. Yeah, I hadn't considered that. In which case, I need to learn more about lambdas, but that's fine. We can generally assume it's probably an anonymous function, and we want to pass that into some sort of Julia kernel. Good, okay. So we're getting there, one step at a time. Okay. So we can run the anonymous function. I think you're right. On out, we get to, the rest of this works just as expected, right? This isn't a big deal. So they also, out was not defined. That's fine. Let's run these 3 lines together and that should work. Perfect. Now, the next thing I want to try is string of my f here. That's not going to work. Okay. But now string of f expression 2 should give me... I'm going to write this out, see what we get. Write function.jl we'll say symbolic function test. Let's say function.jl. And then string here and see what it actually writes out. Okay. Let's take a look at it. So we're going to do vi function.jl. So what actually is this function? Let me remove these comments. So I think we can just delete. Okay. I think we can delete here. Whew, this is some tough code. Okay. So then we do y, which is also fine. Why wouldn't you just put these on 2 different lines? So let x and y at inbound. So then we delete this line, should be fine. Delete that line. No, I can't. Okay, so this line I can delete. That line I can delete. Here we're going to do dt there. Delete those. Okay, the next one we're going to do dt there. dt there. Delete that. This line I can delete. This line I cannot delete. Okay. This line I can delete. This line I can delete. Okay. So this is the actual output here. I think I must have missed something because the indentation is wrong. Crap. Okay, let's try that again. Yeah, here it is. At inbounds begin. Okay. dd. All right. dt there. 1, 2, 3. And then we're going to go over here again. dt there. All right. Delete this. Delete until that. All right. I don't understand. Am I just stupid? I must be missing something. Let at inbounds begin. Okay, maybe. I don't know. I have absolutely no idea. The indentation here is super funky, but that's okay. It doesn't really matter. The point is, we're basically just calling this guy in here out is equal to y squared x. This is fine. That's what we're calling. So fine. It is pre-generated code. I don't know why I'm spending so long looking into this. It doesn't really matter. So what do we do from here? I don't actually know. Yeah, I genuinely have no idea. I want to be able to read this into a kernel is what I want to do. I want to be able to take this function and just slot it right into a kernel. However, when I tried that, I got the error, which was, it got exception outside of test, that there are no method matching get index of expression of int64. So let's do a simpler test, okay? Not with a kernel, but just with another function. So we have myf, right? Which takes in, it should be any 2 numbers. So I think we can do out, and we can do 1, 2. I think this will work. I think it needs an exclamation mark. Out. Okay, let's try that again. 1, 3, and we do out. Sure, okay. Giving different numbers, that's all that matters. Let's create a function, and this function should take in another function as an argument. So we're going to do symbolic test. All right, this is going to take in 3 arguments, out, A, B. Probably also needs to take in my function. Then f, exclamation mark, f. We just do f. Return, or rather, just call f on out, comma, A, B. End. Okay, so let's try symbolic test of out 3, 3. And then f is going to be my f, exclamation mark. Out. Okay, well, it works. Like, we can call it like that. That seems fine. So the question is, can we call it inside of a kernel? Is this any different? Is this any different than the code I just ran? So let's take a look at the code I just wrote. Control D, vi symbolic. Actually, let's just go ahead and remove function.jl. Go into vi symbolic.test. Okay, so we had symbolic test kernel. We read in C, A, B, and F. Okay. So, and we ran F on CAP. Now, there is a bunch of issues with this, actually, now that I look at it. So maybe what we actually want is C of aij and B of ij. Because obviously we're just running this like 1,000 times, or 1,000 or 256 by 2,056 times the way that we were currently writing it. That's fine. And so we need to say C of ij is equal to that, which again, maybe this is okay. I'm not too worried about that step. Let me just try running this again. Include symbolic tests. This is going to give us a similar error. It says it's on line 22. In the example, the function expression is a vector of two expressions. In our case, we didn't have a vector of multiple functions, so we couldn't index function 2. Oh, you're right. I'm calling the function wrong. C is a, b, so f is eval here. Let me see what they have over here. They have eval, and then is actually a vector of a and b. You are correct. So I think we need to put this into a bigger vector here. Thank you for that. That, and then that, I believe. So let's try that. Oh, of course that still breaks, but let's see what we got. No, it's still no method matching get index. Okay, this is okay. Let's see what the issue is. So we have symbolic test of A, B, C, and F. We then pass all those arguments onto the symbolic test kernel of C, A, B, and F. Although I do recognize that these are all kind of a bit mixed up. So let's mix this up again. C, A, B, and F. Down here is A, B, C, and F. Let's do C, A, B, and F again. I'm sorry. I have these very confused. Okay. And then we just test to see if C is correct. And obviously it's not correct. The issue here is that we are... I mean, look, I don't think it has the infrastructure to pass anonymous functions onto a kernel. That's my guess. I don't know if that's actually true or not, but that's my guess. Let me get a little bit more water. Man. So how would we go from point A to point B? How do we go from... Okay, so what's the issue here? So we have the function evaluate here. Is that the same thing I did in the Julia REPL? I think it is. So we said my f, and what is my f? My f is equal to... what's my f equal to? My f is equal to evaluate of f expression 2. So I found x expression, I took 2, and then I evaluated that. I said that's my f. Okay? Let's go into symbolic test.jl. We said evaluate build function c of ab2. F expression of 2. Build function. So wait, where's build function? Build function is up here to compute with the values a and b. So we did that, and that gave us the f expression function, which is here. And then we took the second argument of that, and then we evaluated that. This should be the same. In this case, we didn't have a vector of multiple functions, so we couldn't index function 2. Is that right? Wait, maybe I misunderstood your comment. Sorry. So you said in the example, the function expression is a vector of 2 expressions. A function expression is a vector of 2 expressions. Yeah, okay. So maybe you're just saying we have to define A, B, and C after the fact. Yeah, that could be true. D4D, and then we paste it here. Sorry. I don't think that's going to fix anything. Okay, so we've defined x and y. Those are our expressions. Our variables are x and y. And then we said, our variables are a, b, and c. Then we say c is equal to a plus b. So it's now an abstract syntax tree. We then say f is the evaluation of building our function of c, a, b, where c is our output. But actually, maybe I'm using build function wrong. Let's see, what do we have? Build function. Where are we? Remove line nums. That's not useful. Oh no, there's so much just unuseful stuff here. Building functions. So we build functions and we create another function that's just called toCompute. And where did toCompute go? toCompute is the expression that we're building it. Okay, so in this case, C is the expression. Yeah, C is the expression. A plus B is the set of variables. I mean, I could put this in a vector just to see. Oh, sorry. Let's see what happens. Include symbolic. Oh, wait. This might have worked. It did not work. But we got a step further. Okay, so what's the issue now? Oh no. On line 22, I'm pretty sure 22 is this line, but let me check. 22 is the, that's a completely unhelpful message. Oh, wait. All these problems with wait, eval user input, nested task error, method error, no method matching, set index, a float 64, int 64. Oh. Is this just a floating point error? C. 1 second. Maybe we make sure these... There's no way. Yeah, okay. I just want to double check that this wasn't a floating point error. All right, let's go here and let's do zeros. All right, and let's see what we got. Okay, so we have wait, macro expansion, inline function name. We have initialization .jl52. We have thread run. Oh, this error message is just completely indecipherable. Try it one more time. Okay, so we have wait, macro expression. Okay. Method error, no method matching set index of float 64, int 64. Where is that happening? This is obviously cassette, code.jl, but where is this happening in my code? What line? CPU.22. I don't believe any of these are in my own lines. I believe these are all in, well, I mean, it says cassette, which means obviously this is an issue with, this is obviously an issue with kernel abstractions because kernel abstractions uses cassette to overdub what you write. So what does this mean? I mean, clearly I'm kind of like, punching above my level or whatever that phrase is. I'm kind of like, attacking something that I don't understand, but that's how you learn, right? Okay. So it says, as far as my code is concerned, the line number that I'm concerned with is, it's REPL.jl. Don't give me that. Don't give me any of that. That's completely useless. It's saying CPU.jl, test.jl, symbolic test.jl, 24. Symbolic test.jl 24. And I bet you symbolic test.jl 24 is at variables A, B, and C. That wasn't where I was expecting to get an issue. Let's control C, control D, Julia 1.6, and try running it one more time. Because if it was just an error with line 24, well, this is line 24. So that to me says that maybe it would work if we just didn't have the variables defined in some weird scope somewhere. I don't know. We're getting there. But yeah, thanks guys for coming in. If you guys have any comments, questions, concerns, ideas, anything like that, feel free to let me know. And I'll totally address it. Oh, I'm so sorry for the on there. I'll totally address it as soon as I see it in chat. This guy is just saying line 22. Line 22 is the beginning of the test set. I don't know. What I might do is just comment this out. And then go down here to the bottom and comment this out as well. Try running it again. So it gives me a more exact line number. It is still saying on line 22. Oh no, it's saying line 34. Which is going to be, yeah, of course, the waiting to make sure that the code is actually running correctly. It's fine. Whatever. It is what it is. Okay. I need to think. Yeah, I need to think here. Yeah. What do we do? Maybe we... Okay, let's give it another, I don't know, maybe 10 minutes until 3 o'clock p.m. my time. And then let me just think about this a bit more. Yeah, we need to think about this a bit more. I think if we keep banging our head against this, we can get it to work by the end of the day. I just, you know, I just don't know exactly how to get from where we are to where we need to be. I actually don't know. Again, I don't think kernel abstraction has the ability to read in a lambda function. I would be surprised if it has that ability. I mean, maybe it should, right? Maybe it does. And I'm the one that's being pessimistic here. I mean, we could try just reading in any other function, right? So what happens if we modify this? So it just reads in any function, and we say the function is just going to be equal to a plus b. So let's go over here. F is equal to a plus b. How do we define functions like this in Julia? I don't remember. F of a plus b should be ab equals a plus b is what it is. Yeah, something like this. Cannot define function f already has value. Okay, fine, fair enough. Okay, so let's ignore all this stuff and let's just see what happens if we pass in a function and not necessarily like a symbolic function or anything. We just say f is going to be equal to, function, let me define it up here. Okay, so we're going to define function f. And this is going to read in CAB. And we're just going to say C is equal to A plus B. Yeah, that's what we're going to do. And down here, we're going to read an F. Sure, seems fine. We're going to read an F, and then we're going to do C and AB over here, just removing this guy. There we go, write that. And let's see if that works. Can I define function f? It already has a value. Okay, Control D, Julia, include. Let's just see if it works. I don't know. Could work, could not. I have no idea. So. Okay. It gave me something. The test failed, but it gave me something, which is something. So what is C in this case then? So okay, we were able to read that function in. So that says it's something wrong with function CAB. So we're able to read F in. So then in that case, CAB, it failed, but like it failed in a way that I'm confident that maybe we're going in the right direction, kind of. That was a sentence. So C was just a bunch of okay, that's the issue. Here we're reading in ABC instead of CAB again. It's included again. Dang it. I thought that was the issue, but it was not. Okay. CAB, if A is an array, it doesn't really matter. CAB, they're all reading in CAB. Then we're running symbolic test of CAB. Okay. So then, what is the issue? Why are we getting zeros out? In fact, maybe we're not getting zeros out. Maybe we're only getting. Maybe we're only getting. Let me see if we can actually just print FC out here. So we have all the C's. We have wait for the event, and let's just do print FC, or just print line C. Go down here, add a space there because I just realized the spacing was wrong. Include. It is all zeros. So we're not writing to C correctly, and I don't know why. So let me just go in here and just say C of ij is equal to A of ij plus B of ij. Just make sure this works. Is equal to A of ij. I can't type. I just cannot. Ij plus B of ij. All right, we're going to comment this guy out, run that. We're going to include that. Of course it passes. If it didn't pass, it'd be insane. Okay. So let's no longer print line C, because we know it's going to be all zeros in the other case. Delete that line. And let's see if we can pass in that function. Okay, so we're going to read in C, A, and B, and F. And F is going to be defined as a function C of C is equal to A plus B. And we're reading in C of ij, and A of ij, and B of ij. So we should be calling the plus operation again and again and again. Now, I would love to be able to like take a look at the sort like LLVM code and stuff like that, but I really suck at that. You know, one of my very close friends, one of the primary writers of Kernel Abstractions, actually, yeah, he's super good at this kind of stuff, but I genuinely can't. I always need to ask for help. What I find weird about this is that it's allowing for us to read in the function at all. If it doesn't, you know what I'm trying to say? It's weird that it allows for us to read in this function. Does it need to be another @kernel? Maybe? What happens if we just define this as an @kernel function? Yeah, of course. Well, the expression failed, but that doesn't mean it's wrong. @kernel function F. @kernel function symbolic test kernel. So then we're reading in. Dang. Okay. I mean, I'm really just pushing for this to work, but because I don't want to go through the effort of like actually doing the cassette overdub stuff, let me just take a peek at the kernel abstraction source code here for a second. Delete convolutions in 1D. That's vector add.jl, tutorial world. Okay. See, this is where things get super confusing. And I really, like, back when I started working at MIT, I thought I was going to be able to work on stuff like this, like stuff like kernel abstractions, and I was actually really excited. And then I didn't get that chance, and I was really just sad. Like, I really wanted to work on this kind of stuff, and I never had the chance. And now this library is beyond what I know. And I'm not really sure how to get to where I want to go, you know? So let's see, compiler.jl, compiler metadata. I mean, surely somewhere in this is the list of things that can be compiled, right? Like, you know, like, that doesn't make very much sense, right? Like, there must be like some sort of symbolic representation of each object that is like passed over to something somewhere. Man, I have no idea. Okay. We probably need some of this still open, but probably not all of it. Probably, in fact, we don't need it because we have it on the other browser that's on the other desktop. Okay, so what can we do next? We are trying to see. I'm just going to look at this one more time to make sure I'm not being an idiot. So we do @kernel function. I don't know if we actually need that or not. Do we also need to initialize the other kernel as well? Maybe we need to do that as well. So we do symbolic test kernel, but also we need to say, I mean, it's literally just, in CUDA, I know how I'd do this, right? I'd basically create a device function, right? I don't know how to do that in Julia. I don't know how to create a device function or device kernel in the CUDA idea, right? So, I mean, let's just look up device CUDA, and let's see what we can do. Kernels and launch parameters, so let's look at device. Okay, or not. Right. Okay. But yeah, I mean, that's what I would do. I'd just create a device kernel that's read in to the kernel, and then I just run that. Like, this is what I would do. And okay, so let's do back, calling device function from a kernel. Okay. So global void kernel int. CUDA actually inlines all functions by default, although Fermi and newer architectures do support proper ABI with function pointers and real function calls. So your example code gets compiled to something like this. Okay. Execution happens in parallel, just like normal code. If you engineer a memory race into a function, there is no serialization mechanism that can save you. Okay. let's just keep going. This isn't helping me at all. I need to think. So let's see, it's currently 3:00 p.m. It might be good in a few minutes to kind of like change tact and look at something else. I mean, look, we could go back to the fractal flame stuff that we were doing yesterday. In fact, that makes a lot of sense. But the problem is one of the things that we have to do for the fractal flame method is basically incorporate a symbolic utility set to it. And one core component of the symbolic utility set is that it must be able to be solved in parallel. Otherwise, we can't do it efficiently. Like, what's the world's fastest fractal generator if it can't even be compiled on the GPU, right? Like, what's the point of it? The answer is there isn't much of a point, right? Okay. Give me just a minute, guys. I'll be right back, and then we're going to keep working on this. Again, if you guys have any comments, questions, concerns, ideas, anything like that, feel free to let me know. Again, I'll be right back. Just give me a second. Okay, I'm back. Give me just 1 minute, and then I will keep working on this. I think the next thing I'm going to try is just inlining the function. Ooh, what happened there? Okay, let's just quit, and then let's open it back up again. So yeah, the next thing I want to try is just inlining the function, see what happens. Maybe it's just not being inlined correctly. I'm not really sure. I think I can just do that by inline include. Right. F is not a function expression. Is it not? Wait a minute, what? Why is it not a function expression? Is that because maybe I need to... maybe that doesn't work there. Maybe I have to do it here. One second. Okay, well, I mean, that didn't help at all. I wanted to basically, like, you know, inline it in the kernel is what I want to do. When we pass in a function, maybe someone has done this before. Passing function as kernel abstractions argument. 1 second. That doesn't help. Let's go here to G, see what we can find. Hey Trash Talk, how are you? Does not help. Okay, let's do Julia. Functions, Julia documentation. Of course, I mean, I wasn't expecting this to be easy. I wasn't expecting to just find it, you know? One of the greatest features of Julia is that you can dig out the answers to these kind of questions by yourself instead of making experiments. Let's see what we have. Print line hello world, any function is of type function. I'm sick, but otherwise good. Oh man, I'm sorry to hear that. Hopefully, I mean, yeah, hopefully you get better soon. I know at least where I'm at, it's a holiday today. So a lot of people have off, but, yeah, I don't know if that's true for you, but that would be like a kind of silver lining to the whole thing, you know? Okay. I have no idea. I don't know if you can pass a function as an argument into a kernel abstractions kernel. I don't know if you can do that. What I might have to do is I might have to just send a message to the person who made kernel abstractions and ask, is this something we can do? There's probably somewhere I should ask this, like a discourse or something. In fact, maybe I can just do this on the Julia Slack. Yeah, maybe I could just do this on the Julia Slack. I'm trying to test and I can't, it's just not working. And I don't exactly know why. So I might just put it on the Julia Slack and just let that be that. And see if anybody has any answers. Yeah, maybe that's what I do. Okay, so I'm gonna go ahead and create that, and then, yeah, maybe, what time is it? It's currently 3 in the afternoon. It's gonna take me a few minutes to do that. I mean, I could probably do it on stream, maybe. I mean, it's not a huge deal. Yeah, okay, maybe I can just show the Julia Slack on stream. I don't know, I mean, it's all public, right? So let's just go ahead and do that here. Alright, there should be a GPU channel. And let me just post in the GPU channel and see if I can find anything. Okay, there we are. Somewhat naive question. I'm trying to essentially take a symbolic expression from, let's see, take a symbolic expression from another package, like symbolics .jl or something, and compile that. Well, and turn that into a kernel abstractions kernel. I realize we could probably just broadcast everything. But, you know, obviously there are issues with broadcasting, like everyone knows. But, you know, I will be working with a relatively... Okay. Yeah, anyway. I could probably just broadcast everything. 1 second. I could probably just broadcast everything, but obviously there are small performance loss. There is obviously, but the equations, I don't know how to say that. I will be working with a large number of equations and can easily see large performance hit with this. Okay. So somewhat naive question here. I'm trying to essentially take a symbolic expression from another package like symbolics.jl or something and turn that into a kernel abstractions kernel. Oh wait, I got this wrong. This. Okay. I realize, so with symbolics.jl, I can create a function that I can create a function, I guess an anonymous function like this, and I'm just going to go ahead and put this down. What we have, f variables abc, c is equal to f is equal to eval, something like this. However, obviously, this creates a an anonymous function when I try to read this into KA, it doesn't seem to work with the following kernel. It doesn't seem to work. All right, and we're gonna put this here, and I can provide the error message. I'll say error message in thread. Okay. So let me go ahead and give that error message in just a second. So f of this. I guess I should just put the full code, but okay. So I think this is more of a naive question than that. This here, and then we're going to delete this line for now, and we're going to put it back. Okay, so I'll put the error message in the thread later. Okay, so now the next thing I want to say is the following. Oops, well, it's fine. The reason I think this is even more of a naive question, the reason I think this is, okay. So I took a step back and tried something like this. I didn't mean to press enter. That was an accident. This is why I don't like using Slack, but it's fine. All right, so we're going to put the function here. And then create the new kernel here. Oh, for Pete's sake, every time. Okay, I can't undo that, so I'm going to try to edit that again. All right. I pressed escape. I always press escape because I'm used to using Vim. Okay. So I took a step back and tried something like the following. So here, oh, just for Pete's sake, every time. It's so annoying. Okay, so we do this. We have the function here. Oh, where is it? It's over here. And with the following kernel. Oh, I'll just put the kernel here as well. There. Okay. Okay, where is it? Here. And remove that. Remove that. When I tried the following test set, C it was just all zeros. If I change the line to let's do C of ij is equal to A of ij plus B of ij. Obviously the task succeeds. 1 second. I guess my question is, questions are, has anyone tried using symbolic.jl with kernel abstractions? If so, is there some source code? Look at. 2, should I look? I have some small experience. Hey, Pillar XYZ, how are you? I have some small experience with cassette, and could maybe look at the KA source code to patch this in. If let's see, someone points me in the right direction. All right, so now I need to put the error message. Okay, don't keep me in suspense. You probably just missed the const f. Maybe. All right. Let's see, what do we have here? Dunstable Ramsey. Oh, I thought that was like a gosh darn it type of thing. Okay, so is it that we need a const f? Let's see, what do we have here? So we have function f of CAB. So let's try const f. But where do we put that? Do we have to put this up here? Okay, so now we're going to try this, include, expecting assignment after const. This is where I've forgotten how to use consts. So let's go to Kernel Abstractions. I could just say, happy. Let's see, what do we have here? Function of CAB. Function kernel CAB IJ index. Have you tried setting up as array symbolic expressions instead? Generated Tulio should be CUDA compatible. Hey, do you guys want to have a guest on really quick? Wanna... 1 second. Otherwise, I can hop off and create a call. I mean, Chris is happy to join as well, but like, I'm sorry, I'm an idiot. 1 second. Yeah, so Valentine's a good friend of mine, like, very good friend of mine. So I was gonna see if he wanted to. I mean, Chris can join as well. Improvise Julia party? Yeah, okay, give me a second. Let me see if we can set this up. I don't actually know the best way to do this, so let me... I can set up my audio. Well, okay. We'll wait. He'll be in chat for a second, and then we can just, like, you know, do it either over Discord or Slack. Either one will do. Oh my gosh, I can't speak at all. Oh, I completely bungled this code, though. My word, I'm an idiot. It's been a long time since I did any Julia or Kernel Abstractions development, so this is where I'm a bit behind. Let's see, what do we have here? All right, so I'm not going to show this on stream, but you'll have this up. Call me here. Yep, sounds good. Let me go ahead and turn off the music and see if I can get this to work. Let's go ahead and call. And let me see what I can do. Hello? Oh, okay, so I think you can hear me. Settings? Wait. It'll be back up in just a second. Default microphone. Can you hear me? Nice. Okay, give me a second. I'm sorry about that. Let me see if I can make it so they can hear you. Say something. Hello?
Good evening.
Hey, can you guys hear him on stream? I don't know. Stream's been quiet anyway. It doesn't really matter too much. Okay. Can I also share my screen? Is this going to work? Upgrade to a paid plan?
What?
We can't do... Do you want to change to Discord?
We can. I mean, I also have your stream open.
Yeah, but then there's a 20-second delay.
Well, yeah, okay. Which Discord?
I'm still in the Klima Discord if you want.
Okay, yeah, it's just that.
All right, sorry about that. All right, 1 second. Klima, here we are. Well, actually, I can just call him, can't I? 1 second. Here we are. And then we should be able to start a voice call. Is this working? Hey. Um,
Does this work now?
I'm not sure. I don't
I
think
can't
so.
hear you yet.
I know. 1 second. I'm trying to
What the
fix
fuck?
it. I'm trying to fix it. Voice and video. Let's change this to.
Mm-hmm.
There's no way. How does this work? Oh, it works. Can you hear me now?
Yes,
Hello?
I can.
Nice. Okay. I'm so sorry. Let me share my screen. Screens, entire screen, go live. Okay, so
Yeah,
you should be able to see my
technology.
screen.
Yes, I can.
Okay, let me undo that. And I think we're good to go. So I think everyone can hear you, and I think we're good. Okay, so for those of you guys who don't know who this is Valentine. I've been banging my head against the wall with Kernel Abstractions for the past hour, and he's the one who develops the code primarily. So, yeah.
So it's
I just
all,
wanna ask about-
what Leos is trying to say is it's all my fault.
Yeah, it is entirely his fault. Okay, so I was trying to do something very stupid, and I know it's stupid, but I wanted to see what I could do anyway. And I kind of mentioned it on the Slack issue. Basically, I'm trying to take some sort of symbolic equation and just compile that onto some sort of GPU kernel, ideally kernel abstractions kernel. I thought that I probably shouldn't say anybody's name. I thought that people in the Julia lab were trying to do this before I left. But I don't remember where that went. So I'm kind of like almost 6 months behind in development here. So, yeah.
I mean, Chris had the point that there is some like that symbolics does target Tulio, and Tulio is just another front end to kernel abstractions. So that's a thing.
So
But
should I do that? Is that
no.
okay? Fair enough.
Too many layers of magic. So
Right.
what have you tried so far, and what doesn't work?
All right, so this is I'm being really dumb here, right? So I tried creating at variables a, b, and c is equal to a plus b, and then evaluating that function to be the one that mutates data,
Okay, yeah.
i.e. the second one, and I tried passing that in, and that didn't seem to work. It gave me a huge error message that I have not yet.
What was the error message?
I will give it to you right now if you give me 1 second, and let me modify this as well.
Right. So this. Yep. And then
1 second,
you
I'm
do-
just removing these. Oh, I'm an idiot. 1 second, I can't type right now. There.
where are you constructing your kernel? Oh, okay. Yeah. I see.
It should be here, and then we should have the
Yep.
and then it should just be called down here. I'm not doing the GPU version just yet. I just wanted to
It's
get
fine.
something working.
Oh,
So we included
It isn't even failing on the GPU yet. That is hilarious. Okay.
Right, this is still CPU only, which my assumption would be that eventually. Oh, I'm an idiot. Where's this one? Unexpected that and arguments list.
It's in line there. There's another. There's too many. No, okay, that's fire. That's.
I think that's fine, right?
Okay, yeah. What are you doing?
Well, okay, so this is where things are stupid. So this is where symbolics.jl kind of like. So the way this works is it calls two different variables, right? So this is the one you're mutating. Yeah, it's not.
Anyway, okay. Let's move on and ignore the word.
Right. So this is anyway. Doesn't matter. So if I run this, it should give me the error that we had before, unless I'm a complete idiot. You give it a second. It's obviously doing compilation stuff, but yeah. Okay. So here's the error. I will make it huge and full screen it, and I will show it to you again.
And then scroll all the way up.
Right.
Because this is. Yeah.
So it says it's on line like 24 or something of my code, 29 maybe?
38.
Oh, 28 right here, right?
38 with 3 lines above.
Okay, let's see what that one is. 38. That is, it's just wait on the event, obviously.
Yeah, so that's fine.
But then it says that we have an issue with line 28 afterwards, which is the definition of variables A, B, and C.
Which is just a test set.
Right.
And so if you go further down, so this is the task file exception and then the nested task error. No method matching set index.
Right. I remember seeing that error, but I don't remember where it is in the stack trace. Give me a second.
At the very bottom. You see the red nested
Oh,
tail.
yeah, obviously, yeah.
I know that you don't see syntax highlighting.
I know, I'm sorry. So then,
So
I didn't know what that meant.
So somebody in symbolics is trying to be very cute and clever, and you ended up with calling setIndex on a floating point number.
Right, but I don't see where that is. If this is an issue with symbolics, then I can...
So let's just try calling on the CPU without doing any kernel abstractions in the REPL, right?
Sure. I'm just making this smaller, and I'm going to just do it in this screen. So I'm going to open up Julia 1.6, because that's...
Yep.
And you want to just do kernel abstractions, you said, or do you want to do...
No, using symbolics.
Okay. Yep. Add variables A, B, C type of thing.
Yep.
Sure. And then create a function, so C is equal to A plus B or something.
Mm-hmm.
All right.
And then generate your function.
Right, so then this is, because I'm not familiar with this, the way I have been doing it is, f is going to be equal to build a function of C and then AB or something, right? And this is going to give me, this should give me 2, so we should have f of 1. Wait, am I an idiot? Oh, no. 1 second.
You need to eval that, right? So
Right.
And this is actually already kind of helpful, because now we have the function expressions and we can look at that for a second.
F1, so I guess we're going to say F, I don't know what to call it. This is a really bad name. So let me actually rename this really quick. So we're going to say F is this, and we're going to call it like F meta.
F expert.
Yeah, sure. And then we're going to say F is going to be equal to eval of F expr of 2, 1, which one? I mean, 1 returns, 1 doesn't.
Are there actually 2?
Yeah, so this one will return the value of C, and this one mutates the value of C. So I had been using 2.
I think you want to use 1 then.
Okay.
No, there is no second function. I like, if I look at fexpert, we only printed 1 function.
Wait, what's going on here? So, but here clearly they say f of expr1, and then there's another one down here is f of expr2. Well, here f of expr2, and I just used f of expr2, so I must be doing something dumb here. Unless it's because when I defined this, I didn't define this in an array.
Yes.
No way. That gives me 2 different.
Yes, this gives you a different function.
Oh, okay, sure. Because in this case, C would be. Are you telling me that that's the issue with the symbolic code? That because it now thinks that C is a floating point number.
Right. So in your kernel abstraction code, you're passing in as C a floating point number. Right.
No, I'm reading it in as an array.
Yeah. There you're doing it as an array, but if you then go into the kernel, you're not passing an array to F. You're passing a floating point number.
Correct. In which case, I'm not entirely sure.
Which is why I was thinking about how to do this. Like if you don't pass in an array as the argument to C, then you can do the assignment operation.
Right.
Which might not be what you want, but no.
I was hoping. Well, maybe it should be what I want, right? So maybe you're right. Maybe what I want is.
Yeah. How do you otherwise get the index of what you want to mutate C?
Right. Correct. So you're saying we do something like this is going to be equal to, I don't know, like F of. I don't actually know the syntax, but something like this.
No, you're only missing an equal signs between.
Correct. Yeah. Which was the only obvious thing to write down, and I just completely missed it.
And by the way, you can use a tuple there. I checked.
Okay, good. Because I was confused as to why we needed a vector anyway.
Just need a.
Yeah. So if we change this,
and
I need one.
I don't know if you can use a tuple there, but it should be fine.
We'll see what happens.
And then don't do the 2.
Correct. There you go. Perfect. Okay, so Is this actually the best way to do it, though, is the next question. And the answer is I don't know that.
Now I would need to know what you want to do.
So what I'm hoping to do is I'm hoping to have people be able to write down just any old equation. Like let's say they want to write down f of 1 is equal to p, some sort of value over 2, like just some equation, right?
Yep.
And my hope is that we can create a set of functions and essentially evaluate, iterated function systems, right? Like the fractal stuff.
I know the problem, yeah.
Yeah, essentially I wanted the front end of that to just be people writing down equations. And then I wanted to make it so they write down the equations they want, and then, this is fed into some sort of iterated function system solver, which will, be GPU enabled or kernel abstractions enabled. So this has to we have to somehow get what they type into a kernel without them typing a kernel, if that makes sense.
Yeah, and so there are two ways of doing it. The one way is using symbolics, and the challenging bit is figuring out what to do with the indices. I don't know symbolics well enough to give you an answer there.
Yeah,
how to basically because their approach is more, you're giving us arrays, and therefore we will create these expressions that operate over the arrays in their entirety, which then will invoke Tullio, which will then end up in kernel abstraction land. But what you're more looking after is, right, you want to have a simple function. And one thing you can do is, right, you're doing all of the index manipulation in the kernel, which is correct. And so you can either use symbolics, but the question is, at this point, you could also just use Julia.
So what do you mean just use Julia? So
you define f to be f of a comma b equals
a plus b or something.
Equals whatever your equation is, and then you pass in that f to your function.
Right. So. Right, you're correct there.
Which is basically, right, you're taking the indirections for symbolics, which could be helpful because symbolics can do other optimization and other analysis that are not legal on the Julia level.
Right. The reason I was thinking about going under symbolics is simply because, I was initially going through Impero, and the reason I was going through that is because it provides a lot of nifty plotting tools and stuff like that I can just I can see the abstract syntax tree that I'm looking at way easier.
Yes,
but of course, true. Everything is obviously an abstract syntax tree under Julia as well.
And so what you're doing with symbolics right now is, right, you're calling eval on the expression,
right?
Which in essence is this, and it's so the real question might become more of.
Yeah, do we need the rewriting tools, essentially? Like, do we actually need to leverage symbolics when we could probably just use the Julia infrastructure already existing?
Yeah, and you just for kernel abstractions, like for any map, right? You could have just written a map and it would be equivalent. You're just going to pass in the f.
Okay, so now I'm going to ask another stupid question, because this is one I also couldn't get to figure out. Let's just create a new function, and we're just going to call it. I'm not going to create. It's the same as we just did. I'm just going to write it out in this way because, whatever. F, and this is going to be A, B, end in here, and we're just going to say return A plus B, because this is closer to what I had a second ago. Let's not define this through symbolic, so I'm just going to comment this out. And then I think we can just pass that in.
So the only thing you need to do is you need to undo the tuples here.
Yeah, and I think everything else should just run, right?
Yep.
Oh, okay. Then what was going on before? Let me try one more thing. So f of c, I had it as CAB.
Yep.
Here. Oh, why? Just 1 second. I'm struggling. Okay, and then we say, I'm just going to paste and comment this out. And then we're just going to say f of c of ij.
And is that a dot or a comma?
That is a dot.
And I can tell you without running this code what's going to go wrong.
Okay, well, then I will run the code, and everything's zeros. So what went wrong?
Mutation versus non-mutation.
Correct.
You
So
are indexing into C, getting not the address of C, but you're getting the value of C at this location. And then you're saying, well, C equals, but that doesn't impact the memory location of C.
right.
Because a floating point value is immutable.
Right. So there's no way to send mutable functions. And also, I think you're right in saying that people don't write mutable functions. They're just mathematically you don't write mutable functions typically, right? So
I mean, there are always ways of doing it. You could have created a one-element view.
okay. So in that case, that would be
It's
I
just
to I.
Yeah, no. I think you just can get away with view of C, comma.
Oh, really?
You need to view of C and then comma, and then don't do the parentheses, the square brackets. Just add another comma to after this C. Comma. Yeah.
Well, this I mean,
And now in the F definition, you need to do C and then square brackets. And not there in the C equals. Because right now.
wait here.
Yep.
Of just square brackets?
Yep.
Huh. Okay,
So
well that's something I didn't know.
So you're creating a view, and you could also done a reference.
Right.
There's a referee, which does the same thing, but it's
Okay.
a view is what most people will have seen before, which is a shallow object that has a reference to the array and the indices you wanted to reference in. And since it's a one-element thing with 0 dimensions, you can just use the index operator to get the value of that or to set the value of that.
Right. Yeah, okay. No, I think you're right. I think I was way overcomplicating things. I was using Impero because Impero is way easier to use than symbolics for me because I kind of wrote
You wrote it.
Yeah. But also you're right in that we probably don't need the tree manipulations. We're probably okay. So anyway, I'm sorry for dragging you out like super quickly. I hope everything's doing well.
Everything is fantastic. We just have a big review with certain government entities coming up.
And I'm so sorry.
In half an hour, but that's fine.
Yeah, dude, good luck with that. I'm really sorry.
I wanted to procrastinate on something else anyway.
Yeah, fair enough. Well, okay, I'll mention on the Julia's Slack, it's like, Valentine solved all my issues.
Perfect, ideally.
In 2 minutes. All right, appreciate that.
No worries. Have a great day.
Yeah, we should talk later. Sorry for bugging you again. Good luck with everything. Yeah, let me know how it goes. See ya. Okay, so let me get back to it. So I'm first going to go over here to Slack. Actually, I'm going to first go over here to OBS and turn my volume down to this. I'm going to turn the music back on. Thank you, Silvius Rolando, so much for following. And let's go over here to... where was I going? Give me a second. All right, let me go to Slack and just say, okay, so... let's see. The representation would be like this. That should be... So, we actually saw... You did something like that. Okay, right. So I think we were able to solve it. It was more or less just a syntactic error on my part where I didn't recognize well, I didn't recognize the difference. Mutable and immutable. We'll say, yeah, I didn't recognize essentially how to pass it in correctly. Right. Yeah, okay. I'm just going to say that. It's more or less just a syntactic error on my part where I did not recognize how to pass it in correctly. Thanks again for the help. Okay, good. So, let me just very quickly reintroduce Valentine before leaving. Valentin is one of the head architects of Kernel Abstractions. Genuinely, genuinely one of my best friends as well, but also genuinely nice guy, and super helpful when it comes to the Julia ecosystem and infrastructure, all this kind of stuff. He's always super busy. We're super lucky that he was able to come on for a few minutes there. I'm actually really excited about that. But yeah, if you guys are interested in Julia GPU stuff, you would probably have talked to him or Tim or someone else in the ecosystem. But he's actually he's just an incredible person, and I mean that genuinely when I say that. He's one of those people that you can just have a good conversation with, but also knows more about Julia than anyone else I've met. Okay, I say that knowing fair and well I've met other people in the Julia ecosystem that may know equal to the amount that Valentin does, but I don't think anyone knows more than him. He's just genuinely just a good person to hang out with. I don't know what else to say. Okay, so I'm gonna go here and let's go to our Zernal PP and let's talk about a little bit about what happened there. So Valentin mentioned that we've been using symbolic packages, right? So this whole thing of bringing symbolic equations to GPU code, the fact is we could just pass anonymous functions into the GPU code and it would work equally as well. So what we need to think about now is, do we actually need the symbolic utilities that we've been using for the past few days? And I need to think about it a bit. The reason we were using the symbolic utilities with Impero was because it allows for us to more easily plot and more easily distinguish what the function systems are that we're working on, right? So if you have how do we put this? If you have a Sierpinski function system versus a Barnsley function system, the idea here is that you need to be able to differentiate between the two somehow. But unlike what we were doing in Klima a while ago, we probably don't need to do large-scale syntax tree manipulations, which is what symbolic utils was for. And we're already able to kind of sort of pass functions by reference into kernel abstractions. So I think the next thing I want to do is just kind of quickly test to make sure our addition kernel is roughly the same speed as the last addition kernel that we had. So I'm going to create a new function, which is just the add a lot, which we had at the start. And we're going to see if this is roughly 1.5 microseconds or whatever it was before. Just kind of get a rough order of magnitude approximation here. So what I'm going to do is I'm going to try the symbolic one first, and then we're going to try the non-symbolic version, and we're just going to mess around here. So let's go ahead and grab this guy here, grab that guy there, comment these functions out. So we're going to comment that out, this out, and this out. And I'm just going to run some quick benchmarks and tests to make sure when you pass a function in, you don't get too much of a slowdown. I don't think we do, but just in case. I just now recognize something that I didn't recognize before, and that is that the function I ran last time was a for loop on a GPU kernel, and you cannot express a for loop symbolically except for with a sum, maybe? Okay, let's just put the for loop in here and have it that way. So this is going to read in n as well, and let's just do some quick benchmarks. So this is going to be 4k is equal to 1 to n over here, there, and end. Okay. Again, I'm not saying you should do this. In fact, I'm definitely recommending you don't do this. Just put a random for loop in here, but we're manufacturing a similar test to the one that we had created before. So let's go here, add an n there, and then we also have to add an n, 1 second, down here. So I'm going to add an n right there. Now, we do have the symbolic test done there. I actually don't know the best place to do... I don't know the best place to do the CUDA at profile. So let's do yank to yank, paste down here, and let's just run it twice, okay? And we're just going to include this CUDA at profile, I guess this whole test set. So we're going to do CUDA.appProfile. Oh, this is all on the CPU still. We didn't even try the GPU. Okay, well, let's try this again on the GPU really quick. To do that, I'm going to have to put this in a tuple. And we're going to run it really quick just to make sure it still runs. And I'm also going to create a version that is not in a tuple. Okay, so in here, what we should be able to do is just run it one more time. No. Oh, no. 1 second. I need to think about this. C of ij is going to be equal to A of ij. Oh, sorry. Let's just go ahead and write this. Go over here. I already broke it. We literally had it for 2 seconds, and I broke it already. So we do eval function C of AB. We do symbolic test. Let me just go ahead and comment this out. Comment that out. Write this again. Run it one more time. Okay, and let's see what the error is here. I think it might just be that f only takes 2 arguments now. So maybe what we need to do is just run this. No. Okay, well, we had it working. I might have to look at the VOD actually, which is fine, but we'll do it. Okay. ABNF, and where's this test actually breaking? It is breaking. Oh, it's obviously going to break. Well, first of all, let's just say, obviously this test is going to break. DD, 1, 2, 3, 4, 1, 2, 3, 4. Right, let's go over here, include. Okay. So, we're reading CABNF, 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 CABNF. Everything's being called appropriately, I believe. Okay, so we're waiting on the event. We're doing a symbolic test. So, what is the issue here then? The issue is going to be end not defined. Correct. Here I was thinking there's a problem with the entire infrastructure. It's like, no, you're just stupid. That's fine. I don't mind being stupid. All right, let's go up here and let's just define n equals 2 or something. It doesn't matter. N equals 10. Okay, go in here, include symbolic tests. We had it working. I think it's because we have to put this in a tuple. Here. A, include, there we go, that passes. Yank paste. This is one that doesn't pass, but will pass eventually. And let's just define a new function. Yank 3 yank, paste up here. All right, so let's do some quick benchmarks really quick. Yeah, let's do some quick benchmarks. Right, so we're gonna put the for loop back in and do some just very stupid benchmarks. I know they're stupid, but we're gonna do them anyway. So for k is equal to 1 to n, and then in here, there, and in here, and then we're gonna pop down here, do the symbolic test here with an n equal to 10. 1 second, and then another symbolic test with this equal to 100. I mean, yeah, it's fine. Okay, so let me just do a couple quick benchmarks and see what we can do. And maybe even I have this in the global scope. Would people be pissed if I did? Let's just put this whole function in main. Not doing a test set this time. Just doing function main, and then we're just going to do CUDA@profile main. Main. Okay, now the next thing is I need to actually run this on the GPU, which I haven't done yet. So let's do that. Yeah, let's do it. Okay. First, let's run this and just make sure it runs. It just... Calling CUDA@profile only inform... Oh, right. We don't have the add. It's fine. Okay, so now let's go ahead and do this on CUDA. Control D, vi vec add dot slash ka.jl. Move down here to the bottom. D, and now let's just do it. So we're going to do if has CUDA GPU, All right. End. And we're actually just going to move everything to the GPU. So we're going to say D of A is going to be equal to Q array of A. And then we're going to do Q array of B. And then Q array of C. Okay. Then we're just going to do the same thing we did just a second ago up here. So just yank 2 yank, or yank 5 yank, and paste it down here. And we're just going to run it really quick to make sure it runs without any problems. Right, this, go over here, quit Julia 1.6, run. There should just be an include, right? We're going to get a warning about the CUDA app profile again, but it should in principle run. And we'll see what happens. Let me get some water. Okay. Yeah, so we'll give this a second to run. And then we're just going to do the CUDA app profile again. So Control D. Now we want to run just nsys launch, basically the same thing we ran before. So it's going to be nsys launch Julia. Actually, you probably want to do builds Julia 1.6 slash bin Julia. And now we're going to do probably just include. Should work. Give it a second to see what happens. I actually am quite curious to see what this report is going to look like. And we're just going to see how long it takes. Basically, this time we're calling a symbolic function. And we're just going to see what it looks like. We're looking at like 1.5 milliseconds, microseconds, seconds. I think it was microseconds, which is kind of too fast to profile anyway, but whatever. It's what we're doing. And then we're going to modify this again so that it just basically runs the same code, but it's going to have a slightly different thing to profile. So here we're going to do symbolic test, and this time we're going to call this guy, and our F is going to be defined not symbolically this time, so we're going to comment all of this out, and that out as well. Move up here, and we're going to define our function there. Perfect. Okay, let's go here, and now we're just going to run include again, and this should provide report 2, hopefully, .qdrep, and then we're going to do the same for report 3. I'm just checking to see if this matters any, like the fact, I guess that doesn't really matter. So this should be report 2.qdrep, perfect. Let's move up here and do the mutable version here. Okay, so one more time. G. Okay, everything else should be fine. I hope. So let's give this a go. We'll take a look at the profiling results after this is done, and just look at report 1, 2, and 3 and see what the differences are between just a simple vector add 100 times. Okay, so we're going to go in here, Control D, and now we're just going to run nsite sys report 1.qdrdb. Okay, this is right. Definitely different than before, but that's okay. So right click, show an events viewer. Obviously the CUDA memory allocate is going to be the biggest bit here, but I'm actually trying to find it. Where are we? All right, give me something. Is that what these are in here? Wait, here we are. Wait, is that all we have? No, surely we have more than that. All right, let's just zoom in. Where is everything? Okay, well, we have CUDA memory allocate, CUDA context synchronize, memory allocate, yep. Each device, CUDA stream create. This is 17 microseconds. We are, where, so memory allocate, copy H to device, memory allocate, H to device, memory allocate, mem copy, CUDA stream. Must be that one then, right? CUDA API, show an events viewer, CUDA. These are all allocates. There is no computation being done here. What is this? That's CUDA mem copy H to device. Where's the computation? Like some computation happened. This? No, this context synchronize. Okay, CUDA stream again, 12 microseconds. Okay, I need to look at this again because quite frankly, these results are not, they're not exactly what I was expecting or hoping for. So, but it must be this one, right? Okay, so let's just try running the... I need something more complicated here. Essentially what I'm trying to figure out is, does the symbolic version of this kernel take longer than the non-symbolic version of this kernel? So the easiest way to do that is to run this one more time with a non-symbolic version. So let's go here and just say C of ij is equal to A of ij plus B of ij. So it's going to be C of ij is going to be equal to A of ij plus B of ij. This is such a bad profile. Yeah, I'm not doing very good with the profiling here. I need to think about a better test. Okay, let's go here. Over here, nsys, nope. All right, 1 second. nsys launch, Julia, and then run the last include. 1 second, I'm just checking some things over here. Wait, I'm getting a few notifications. Give it a second to create the symbol file, and then we'll take a look at what should be report 4.qdrdp. And I'm actually just going to close Julia and open it back up again for another run. Oh, this is stupid. I'm an idiot. I'm such an idiot. Remove report 4.qdrdp. Let me comment this line out. Okay, let's try this again. nsys launch. Actually, let's just remove all the reports. So remove report. Should just report all of them. Okay, we're just going to do it one at a time. So first is going to be the simple version, nsys launch. Include this guy. We're benchmarking too much. I know we're benchmarking too much, but we should still be able to see at least the compute kernels going on. Oh, this is all just doing C is equal to A plus B, so we should still be able to test it, right? Okay, let's not worry about that for now. Let's just do one at a time and see what we can find. Okay, so then the next one, what we want to do is read in the mutable version. And we'll do that in a sec. Error. What? Don't give me that. int64 has no field j. Why are you in int64? Okay, well, let's just go ahead and control C here, and let's just run Julia 1.6. Let's run the code one more time, get that error message again, and try to figure it out. Again, guys, if you have any comments, questions, concerns, ideas, anything like that, feel free to let me know, and I'll totally address it as soon as I see it in chat. It's been a super quiet day, like, honestly. So anything you say, I'm definitely going to see. Okay. So it says symbolic test 67 is an issue here, but the issue is basically that int64 has no field j. Okay, that is going to be on line symbolic test 13. That's here, right? So for some reason it's seeing C as a int64, and I don't understand why. So maybe we... Oh, it's seeing F as a symbol. What? Let's just comment a bunch of stuff out. There. So we've removed all the F's, and this should just run. Does not. Okay. Why does it not just run? CAB and F. CAB and F should be fine. Let's just try the CPU version, see if we can get that to go. There. Run that. Of course, that still breaks. So we're running symbolic test CAB10F. So we're waiting for that event to finish. C clearly is just a set of zeros at 256, 256. So where is the Why is it thinking it's an int64? Int64 has no field j. So we're waiting main. Int64 has no field j. What did I do? Let's comment this out as well. And that out as well. Control D, include, try it again. Ah, you're right. Thanks for that. Control C. All right, so let's comment things back in. Appreciate that. Okay, it's still fine. Yeah, so let's go ahead and DD here, remove these guys. I can leave the rest as is, I think. Comment this back in. Okay, go over here, Control D, nsys launch, include. This should give us report 1, maybe report 2, but we'll fix that. And then we can go from there. Let me get some water. Yeah, it's been a while since I've, like, this has been probably one of the quietest streams I've had in a long time. Load error, F not defined, but what, oh. It doesn't matter, let's just define a few Fs. Control D, remove, report, star, nsys launch, include, and go from there. It's been a super quiet stream, it's insane. It's one of those things, I've been wondering, maybe it's because it's in the science and tech category instead of software and game development category. I don't really know. I really don't know. But yeah, we'll see how this goes. I'm expecting it actually to be quite quiet here on Twitch for the next few weeks. And then I'm really, really hoping that the next video that I put out just like blows people away. And that's why we're spending so much time on this type of stuff, right? Like maybe it doesn't. Maybe it's actually not super useful at all. I don't know. We'll just see how it goes. Okay, so the next one I want to run is this one. So let's go ahead and comment that out, write that, go over here, nsys launch, include. Try it one more time. I mean, again, I'm also pretty sure that the next video, I just don't think it's going to do super well on YouTube. But we'll see. Okay, give this a second to run, and then we'll just run each of these cases individually, and go from there. I have nothing to say. That's fair. Like, again, I should probably just stop saying, like, the stream's been really quiet. Like, I should probably just not say that kind of stuff. Because, like, it makes people feel like they're obligated to say something. It's like, you're not obligated to say anything. Like, when I watch streams, I also lurk almost all the time, you know? I'm actually, like, kind of, like, I don't know, I'm socially anxious to say something in streams, you know? Okay, we're going to give this a second to run, and then we should get another QTREP file, and then we should have one last one, which we'll use the symbolic utils for. So let me go ahead and prep that file while we're waiting. Here, go in here. There. Symbolic utils here, and there. Okay, so the last thing we need to do is Control D, run it one more time, open this up, and include. And we're just going to take a look at these 4 files and see how they're changed. Flying Squirrel 0, thank you so much for following, really appreciate it. Okay, but once this is done, we then have a bit of a discussion about what we actually, like, how we how we envision is probably the word I was looking for, the future of this code base looking, and what we actually want the symbolic utilities to be used for. The truth is, I'm always a little bit afraid of using, like, big Julia libraries and stuff like that. So, yeah, because there's just probably a lot of, like, just stuff in there, you know? Okay, so all these have been done, so let's run nsite sys on report 1.qtrep. Okay. We're going to take a look at the CUDA API, and we're just going to take a look down here, show an events viewer, CUDA stream, This one takes 16 microseconds. The rest is just allocates. So this is for A, B, C, and then event synchronize. So it looks like 16 microseconds is what we have here, which again, kind of, I don't know, I'm not, there's something wrong here. 16 microseconds as well for the CUDA stream. And then here we have show an events viewer. Oh, I'm looking at the wrong events. Okay. I'm understanding now. Right. So we need to open report1.qdrep. CUDA stream 16 microseconds. File open report2.qdrep. CUDA stream is 16 microseconds. It should all be the same. I'm just double checking. Open report 4. Sure, we'll do that one first. Show an events viewer 17 microseconds. It doesn't matter. Okay, so now we're going to do open report 3, and then we're going to do 15 microseconds actually. So this says to me that passing a vector in and mutating everything seems to be the fastest one, but again, it's not by much. So it is weird though, because we called the kernel twice. So I was expecting to have 2 different CUDA streams. Let me take a look here and see what we got. So this is going to be highlight selected on timeline, QStream create. Oh, I lost it. Okay, so let's zoom out a little bit. It's just because we called it twice. I really thought it would have created 2 different, you know what I mean? It should have created 2 different like calls, you know? Anyway, the point is there isn't one that's like way slower than the other ones. The symbolic utils was maybe a little bit slower, but I don't know, like that's hard to say here or there. Okay, so here's the next question we have to ask, and we have to answer or whatever. It's, do we actually need the symbolic utilities and stuff in a separate package? Like, do we need symbolic utils.jl or symbolics.jl, or could we just focus on everything being, now that we know we can pass essentially function pointers in, why can't people just write function pointers? Which is a fair point. So before, we'd spent a lot of time on the symbolic utilities and all this kind of stuff because I don't actually know. Maybe it's okay to just leverage Julia's existing tools and go from there. But what I will say is right now, I think this is an okay place to stop. We've kind of looked at a bunch of these different utilities, figured out how they play into things. I think I'm just going to call it for today. And try to figure out, like, just write down in a notebook, like, what needs to happen, where we need to go from here. I think tomorrow we'll be back to working on fractal flame stuff instead of symbolic utility stuff, and I think we're going to try to incorporate some sort of symbolic thing into the fractal flame method that we already have. I think that's where we're going to leave it. So I think the overall answer of how do we take symbolic equations and put it into GPU code, I think the simple answer is that we just use, that we can just go ahead and use Julia's existing infrastructure just to write essentially f of x, y, z, or whatever, and just read that directly into a kernel, which is the simple answer, but hey, if it works, you know? Okay, so that's it for now. Let me see who's live and who we might want to raid at the end of stream. Looks like the only people live are Tim and Lana again. If there's somebody that you want to raid at the end of the stream that you know is good and streams around this time zone, let me know. Otherwise, I might just go ahead and call it. Okay, actually, that's what I'm going to do. I'm going to let you guys decide who you want to go to after this. So that's it for today, guys. Have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. And I'll see you guys around next time for the next episode of Simuleos, which will be tomorrow from 5 to 8 o'clock p.m. Central Eastern Standard Time. So slightly after the end of this stream. Thanks again, guys, and I'll see you next time. Bye, guys.